Hello and welcome to Vector Fields, from kindergarten to university. What is a field? I'm sure you've probably heard it somewhere on the internet before. What I have here is a children's toy from a dollar store. Probably cost about exactly $1. And inside of here we have little iron filings, sticks of iron. And when you see I put this magnet here, you can see the filings all around. And when I pull the magnet straight up, some of those filings point straight up, so they look like little dots. This is an example of a field. Here we see the magnetic field, or at least what the iron filings show of the magnetic field. The way in which the screen is cleaned is with another magnet. And you see when the two magnets make contact with each other, one magnet can move the other magnet. And when I tried to push the one magnet against the other, you can see it recoil. So you can see that fields are so simple that we use them for children's toys and can have children draw on them, or write on them, or play with magnets on them. If we look up fields in YouTube, everyone seems to have a video on fields, but what are they all saying about fields? Where do they step into them? Usually, the demonstration of a field is just to show you a picture of a field. They might use it to explain something, but overall, it's kind of hard to explain what a field is. But that's what we're going to do today. Here I have a wire-controlled robot arm kit. In this kit, there are wires. Here is one such wire. If we were to plug this wire in, a current would flow through it. And when that wire has current flowing through it, an electric field is generated. We could imagine that at some point above this wire, we could detect that electric field. And that is exactly what we are going to do. So in order to solve the problem, let us first write the problem. The problem being that we are trying to find the electric field, a distance z, above one end of a straight line segment that we're calling L, which carries a uniform, it's all the same, line, it's along the line L, charge, a uniform line charge, otherwise called a current. Let's call that lambda. So the first thing anyone should do when doing a physics problem is, let's put it here, step 1. Draw. So we have some line segment. It is a straight line. It is a segment. It is our wire L. Above the wire, somewhere, like the camera, there is an electric field. And we are going to say at some distance z or z. And I'm going to use my own little notation to say that this is carrying a uniform line charge lambda. So what we are going to do is we are going to learn all about triangles and circles. And we're going to do that from kindergarten to calculus. So let us begin at kindergarten, and we will return back to this problem after we complete grade 6. Hi, welcome to Vector Fields, from kindergarten to university. We're going to learn all about vector fields, and we're going to start at kindergarten and we're going to move to university. Pretty clear. So let's start out by going to kindergarten. Hi class, welcome to kindergarten. This is a triangle. Triangles look like this. This triangle is green. Some triangles can be blue, or orange, or yellow, or they could be small, or they could be big. This is a circle. Circles look like this. This is a blue circle. Circles can be different colors. Here is a green circle, a red circle, a purple circle. Circles can be small, and circles can be big. Hi class, welcome to grade 1. Do you remember triangles and circles? Let's look at the triangle. Triangles have 1, 2, 3 corners. If we look over here, circles have no corners. Triangles also have 1, 2, 3 sides. If we look over here, circles have no sides. Hi class, welcome to grade 2. Do you remember triangles and circles? You do? Awesome! Let's try and find circles and triangles in real life. Let's start with the triangles. The shape of some trees is like a triangle, that's right. The roof of a house looks like a triangle. Those big metal towers that bring electricity to your house, if you look at them, they look like they're covered in triangles. And also mountains. Mountains are like big triangles in the distance. Now, let's try and find circles in real life. One of my favorite circles in real life is the moon. Another circle that you can find while still using that telescope could be the planets, like Jupiter. What about your eyeball? Your eye has circles. It has the circle of the iris and the circle of the pupil. And when you draw a picture of an eyeball, you draw a circle. Hi class, and welcome to grade 3. First, we're going to do a recap. That means we're going to remember what we learned from the past. Let's start with triangles. Do you remember that triangles have 3 corners and 3 sides? That's right. And what about circles? How many sides and corners do they have? That's right, 0. Now, we're going to learn something new today. We're going to learn all about grids. This is a grid. A grid is like lined paper that you use to write your name and practice your printing. But it also goes up and down. So you can draw pictures with it because each square is the same distance as it is left and right as it is up and down. So you could draw something that's like 5 squares this way and 5 squares this way and 5 squares this way and 5 squares this way, and you would know it's a square because it has the same amount of squares inside. That's what a grid paper's for. Let's start with a real life example of a triangle. Let's start with one you might find at a playground. What is this child playing on at the playground? Can you guess? That's right. That is a slide. I have another question for you. What is it called when a baseball player stops moving in the sand on their way to a base, but they keep moving? What would someone call that? Maybe the announcer calls such a thing. One thing they might call it is a slide. Well, if this is a slide, and that's a slide, what if we also just said that when the boy climbs up the ladder to the slide, let's also call that a slide. Since we have 3 different kinds now, which is very confusing, we have to give them new names, okay? So we call the one that makes him run across the bottom a horizontal slide. It's called horizontal because it's like the horizon, which is like the distance, which goes all the way along this way. The other slide is vertical, which means to go up. And for the last one, what we usually knew as a slide, we're now going to call a diagonal slide. Another important thing that we need to learn is an important thing about those circles, that they turn. Like a clock. Your clock can turn. The arms on the clock turn. Hi class, and welcome to grade 4. Do you remember triangles? Of course you do. Here is a triangle. It's just the outline of a triangle. I have an important question for you today. How much space is inside the triangle? In grade 4, the way we solve this is with the grid. Imagine that you want to paint a triangle on your bedroom wall. So, this white line is actually tape that you've put up to outline where you want to paint your triangle. Now, you need a certain amount of paint to fill the triangle. How much paint do you need? We have some squares inside this triangle from our grid. We're going to count up all of the squares. The grid has some squares that are complete squares, and we're just going to count them first. So we have 1, 2, 3, 4, 5, 6. 6 full squares. Next, we're going to count up all of the half squares. So we have 1, 2, 3, 4. 4 half squares. Well, half of a square is 1. 2 half squares is 1 square. So if we have 4, then that means that we would have 2 whole squares. So we're going to have 6 whole squares and now 2 whole squares. Next, what we're going to do is we're going to put little asterisk stars on all of the other spaces. And we're going to apply a rule. Mathematics is all about rules. And here is one of our first rules. If the star is less than half, we count 0. If the asterisk is in a space which is greater than half, we will count 1 space. In this case, we have 2 spaces which are greater than half. So we're going to count 2 whole spaces. We also have 2 spaces which are less than half. So we're going to count 0. So in total, 2 extra whole squares. So we have 6, 2, and 2. 6, 7, 8, 9, 10. This triangle has an area of 10 squares. Hi class, and welcome to grade 5. Do you remember triangles? I know you do. This is a triangle. We're going to do something really special today. Instead of just counting 1, 2, 3, we're going to say A, B, C. And we're going to name this triangle the triangle ABC. The next important thing that we want to do in grade 5 is we want to learn how to take triangle ABC and we want to learn how to move it to a different space on our grid so that we can make an identical triangle that's also triangle ABC, but just having been moved. We also want to be able to take that triangle and spin it so that we can rotate it in different ways and it's still triangle ABC. Hello class and welcome to grade 6. Today is a very important day. Today we are going to learn how to plot. So, we've had this grid paper since grade 3. We're going to do something special with it today. What we're going to do now is we're going to take a number line and we're going to apply it from the corner and we're going to stretch it out this way. Next, we're going to take another number line, but we're going to make it go from the bottom to the top. And we're going to call this space our plot. So all of the little squares in the grid now belong to these two arrows, and they count. They count how high the line goes up, and they count how far this line goes out. Next, what we're going to do is we are going to apply a little point somewhere on our plot. This point is a distance from the axis, a few steps, and then it goes up from there a few steps. So we got 4 points to the right, and then we will have 3 points up. So what we will say is that this point has a coordinate space. We will name him A. He is point A now, and he has the coordinate, or the coordinate pair numbers 4, 3. The 4 represents how far from the right he came from the point that we call the origin. It's the point where the two number lines meet. 1, 2, 3, 4, 4. 1, 2, 3. 3 represents how high up that point went. Next, what we're going to do is talk about more ways to draw arrows on a grid. So, the way we just drew that was one type, and we will get to that type. But first, let's talk about acute angles. Acute angles are angles that are less than 90 degrees. An angle is those two lines pointing in a certain direction with their bases touching. So they start at one point and they go out in different directions. And those two directions, if they're less than 90 degrees, it's called acute. What is 90 degrees? That's the first thing we drew. That's a right angle. Next, if there's the acute, which is less than the right angle, what comes after the right angle? This we call the obtuse angle. The acute angle is less than 90 degrees. The right angle is 90 degrees. The obtuse angle is more than 90 degrees, but less than 180 degrees. 180 degrees is what we call a straight angle, or a straight line. A straight line is 180 degrees. So if we have less than 90, 90, more than 90, 180, what's next? More than 180. That we call a reflexive angle. So all together then, we have these angles. Now, imagine that we were to draw a line from one point to another. We would end up with a bunch of triangles. Let's do that and see what we get. The first line goes across the straight angle, giving us a straight line. A line across the obtuse angle and one across the reflexive angle give us identical type triangles, obtuse triangles. A line across the acute angle gets us the acute triangle. And last but not least, going across the right angle gets you a right triangle. Now we need to talk about triangle types. Here is a triangle type. An equilateral triangle. An equilateral triangle has 3 equal sides. That's what it means. Lateral means side, equal means equal, equal, lateral, equal sides. 3 sides equal. If the sides are equal, the angles are equal. 180 degrees, that's a triangle. 180 degrees divided by 3 identical angles, 60 degrees each. Next, when two sides are equal, that means two angles are equal, this we call an isosceles triangle. And finally, the last one, when no sides are equal to each other. That would be what we call a scalene triangle. Okay, welcome back. So, let us continue on with working through this problem. Let us begin with what we learned in kindergarten. In kindergarten, we learned about triangles. So let us make one such triangle. This is a triangle. This is a triangle. In this problem, we actually also have triangles. This is the line, and it's carrying charges. We could pick some point here, and it will have some electron with some charge Q. It will be some distance, let's say x, along the line L. And so there will be, at some point here, let's call it P, there will be an electric field at that point, P, caused by the line's charge down here at Q. And we have here a triangle. So we know from kindergarten that that is a triangle. Let's do grade 1. Grade 1, we learned there are 3 sides to a triangle. 1, 2, 3. 1, 2, 3. Confirmed this is, in fact, a triangle. 3 sides. In grade 2, we looked for real-life examples. We have here a real-life example with a real wire and a real electric field, which is at some point, say at the camera, above the end of the wire, which is a real thing. This is a real-life example. Grade 3. In grade 3, we learned about grids. Here is a grid. We also learned about slides. So here is also a slide. In grade 4, we learned how to find the area. In grade 5, we learned how to label a triangle. So, like Z, L, and let's say R. Let's redraw it. In grade 6, we learned how to plot. So we draw one number line in this direction. Let's call this the X number line. And we draw another number line up from here. Let's call this one the Z. And we learned how to put objects on our plot, like a triangle. a triangle that is Z, X, R, or X, Z, R. In grade 6, we also learned how to find different points. Like we found a point that was the point 4, 3, which was 4 to the right, 3 up. In this case, we are going X amount in the, let's put a hat on him, in the X direction. And let's put a hat on him and say that we are also going Z amount in the Z direction. So if we were to go back and say that this was the point P, then we could say that this is going 0 amount of X and Z amount of Z, or Z amount of Z, Z amount of Z. Z is also, that this point here would be Q, where we went X amount, Z high. We also learned about right angles and right triangles. So this is a right triangle. So then this is as far as we can get with going from kindergarten to grade 6. So let us go on to grade 7 through 9 and see how far we can go through this problem after that. Hello class, and welcome to grade 7. To get started in grade 7, we're going to draw a line on our grid paper. Next, we're going to imagine that we place some chalk at the end of our line, and then we're going to spin the line. What happens? It makes a circle. A circle with a line through it. That line is called the diameter. Half of that diameter, starting at the center and going to any part of the circle, is called the radius. Let's make a radius. The area that we made in the circle is called the sector. And the line on the circle we call the arc. If you continue that arc all the way around, that's called the circumference. Now that we have all of this information, we can start doing some real math. One thing we can say is the diameter D is equal to 2 radii. It takes 1 radius would be half, so 2 radius would make 1 diameter. 2 radius equals 1 diameter, D equals 2r. Or you could say the radius is equal to 1/2 the diameter. R equals 1/2 D. Now, here is a very important math lesson. This one will be carried all the way to university, so hold on to this one. This is the circumference of a circle divided by that diameter should always be the same. That's what it would mean to be a circle. A circle is that which is circular all the way around, such that when that diameter was spinning, it always is the diameter. It always touches the outside of that circle. So, no matter whether you shrink or grow the circle, the ratio, the circumference divided by the diameter, will always be the same number. And that number we call pi. Pi is about 3.1415, and it goes on and on and on forever. It would basically mean if you're to roll this wheel, this circle, as if it were a wheel, it would take about 3.14 rotations. But the more you zoom in to find out exactly what that number is, you will never really find it. It's not quite perfect. It never quite rolls on 3.14. So, we get a very special number we hold on to forever. Pi. It's the circumference divided by the diameter. So one thing we can say is the circumference. If we want to find the circumference, all we need is to take pi and times it by the diameter. If we don't know the diameter, but we only know half the diameter, then we would say the circumference is equal to pi times 2r. Okay, next, we're going to do something kind of interesting. We're going to take this circle and we're going to make it into a bunch of sections. So let's do that. So we have a circle with a bunch of sectors in it now. We're going to now take this, we're going to split it up so that it kind of makes a rectangular shape or a trapezoidal shape. We're then going to turn this into a type of trapezoid, and then we're just going to shift the trapezoid back into a rectangle. So this rectangle would represent the area of the circle, because it was all of the space inside the circle approximately, because we cut off those little bits at the top. So what do we have? The bottom and the top of the rectangle are half each, or half the circumference. So we could say that the bottom, the base, is the circumference divided by 2. What was the circumference? 2r pi, or pi 2r, whichever. Divide by 2 now. So the base is pi r. Next, we have the two sides. Those came from the sector's radius. So they're all r. Both sides are. The area of a rectangle is the base times the height. R times r pi. The area of a circle approximately is pi r squared. We are now going to do the areas of triangles. This triangle has this base, and this triangle over here has this base. Now the question, what are these triangles' heights? For this one, we can just simply go from the tip of the triangle straight down, and we can see clearly that we're making ourselves a height and a base. On this side, the height is a little bit trickier. The height is the exact same principle, but you don't come down to the center of the triangle, you just come straight down. The height and the base of the triangle. Now we can't have the area be base times height. That's a rectangle. But these triangles represent half of squares or rectangles. So we say that the area is 1/2 base times height. Alright, my grade 7 class, let us continue on learning a few new things. Let us take our grid paper and let us draw 3 points on them. We're going to label the points point A, B, and C. What we want to do here is we're going to draw a line from A to B. Next, we're going to make a line coming back along this line that is not longer than half. So somewhere between this A and B, somewhere between half and B, we're going to just pick a point to stop. We're going to call that D. Now, we're going to make a circle that goes around D, which touches C. The circle also touches the line AB. And on that point, we're going to make another point called E. We're going to draw a circle of exact equal length to the one around D, around E. If we now draw a point at the very top of that circle, that would give us the point F. If we draw a line between C and F, and erase everything in between, what we will find are what we call parallel lines. So this is a way of finding parallel lines using dots and lines and circles on your grid paper. We say that line AB is parallel, and we say that with two straight lines, parallel to FC. Now we need to talk about another type of line interaction. So we're going to start with a point, and we're going to label it A. Let us draw a line off of A, and wherever we stop, we will call that B. Let us draw a circle around B. Where the line and the circle meet, we will draw a dot and call that C. We draw an identical circle to the one around B around C. Where the two circles touch each other, we're going to make the points D and E. We will then draw a line between D and E. So we clear off the circles and we see these lines are perpendicular. So we say line AB is perpendicular to line DE. And we draw that with a little upside down T, a perpendicular picture. Okay, next, we want to take angles into account, and we want to be able to cut angles in half. How will we know what half of any angle is? Let's try. We make a point A. And again, we draw a line from A, but this time we draw a second line from A. So we get a line to B and a line to C. If we draw a circle whose middle point is on A, and whose circle, the outside circumference, touches points B and C, then what we can do is draw that identical circle on points B and C. Where the circles of B and C touch, we can mark the point D. If we now draw a line between D and A, that line will be half of the angle BC. And so the line, we say, bisects, as in cuts in half, a section by two sections, two halves. It bisects the angle. So what we call this, after we remove the circles, is an angular bisection, or an angle bisection. Okay, grade 7, we're almost done, but we need to introduce a new concept. Here's what we're going to do. Remember in grade 6 we learned how to plot? That helped us when we wanted to come out in this space over here that was to the right and up. But what if we started at that point and put that point in the center so that we could go to the left and up, or to the left and down, or to the right and down? That is what we call a quadrant. Quadrant meaning 4 parts. We label the quadrant in the way in which a line starting on the x-axis and going counterclockwise would go. So we count them 1, 2, 3, 4. So let us practice with this quadrant. What we're going to do is we're going to have point A, B, C, and D. A is at point +2, +1. So 2 to the right, 1 up. B is at -2, 1. So it's 2 to the left and 1 up. C is at -2, -1. So it's 2 to the left and 1 down. And D is at +2, -1, which is 2 to the right, 1 down. Hello class and welcome to grade 8. Look at our grid. We've made the squares a little bit smaller. That's because we're getting into a little bit more detail. Are you ready for that? So, one thing that we've been talking about this whole time are triangles and circles. But we also learned circles, that area of a circle, we could identify with rectangles. Let us talk about a certain type of rectangle, a very special type of rectangle. What is a special type of rectangle? Do you know? That's right, a square. A square is a special rectangle, It's special because it's equal on both sides, the top and the bottom, and the two sides. All four sides of that rectangle equal makes it a square. Let's see examples of that. We take the rectangle 16 by 1. It has 16 squares that go to the right, and it is only 1 square high. What is the area of this rectangle? The base is 16, the height is 1, 16 times 1, the area is 16. What happens if we cut this in half and put it underneath the other half? We would get another rectangle, one that is 8 by 2. Okay, 8 times 2, 16. The area hasn't changed, so we're okay to do that. So let's do it again. Let's cut that in half and stick it all around to make this into a better shape. What's the shape that we know? 4 times 4. That is a square with 4 long, 4 high. 4 times 4, 16. The area is the same. So we say that some numbers can factor into square shapes, or some numbers can factor into perfect squares. One thing that we can do, this is a very important historical identification between squares and triangles, is Pythagoras' theorem. If we take our 4x4 square and we move it over here so we get some space, we could add in a 3x3 square next to it on its side there. This leaves open one space that could be filled by a 5x5 square. So, what happens when we set up our squares in this triangular pattern? Well, we get a scalene triangle. The scalene triangle of sides 3, 4, 5. How do we get 3, 4, 5 from the scalene triangle? That's Pythagoras' theorem. We can see that the area of 4 and the area of 3 in square form gets us the area of 5 squared, the square of 5. So we can write a squared plus b squared equals c squared. Hello class, and welcome to grade 9. Today we're going to start with circles. So we have here a circle with a center point called the origin. So we're going to label it O. If we draw a line from the origin to the circle's edge, we can label that point P. If we draw a line that only touches the circle at point P, we can say that that is a tangent line on the circle. This tangent line on the circle we will label the 2 points A and B. If we then draw lines from A to the origin and B to the origin, we have a triangle. In fact, we have 2 or 3 triangles depending on how you want to look at it. Since the line AB is tangent, it only touches point P at that one point, we can say that AB, line AB, is perpendicular to the line OP. Tangent lines on circles are perpendicular. We say that if AP, the line AP, is equal to the line BP, then we would also know that the origin to AP, that angle, is equal to the angle OBP. And then it would be possible that we would know that the lines O to A and O to B are equal. Next, we're going to take this circle and we're going to draw a line through it, but we will not make that line go through the center. That is what we call a chord. So we set it up such that the line goes through the points A, B. And those points do not have the line go through the center of the circle. If we find the center point of our line AB, let's call that Q. Let us now draw a line from Q to some point S somewhere in the circle. So we say that if AQ is equal to BQ, then the line QS will pass through the origin O. Okay, let us continue on with our circles. So, we take the circle and we start at the origin, and we draw two lines in different directions to the edge of our circle. Let's label them P and Q. Now, standing on points P and Q, let us merge them to some other point called R somewhere on the circle. So now we have two different angles. We have the angle POQ and PRQ. They happen to share the same arc. That's exactly what we've set up by doing this in this fashion. So we know that P to Q is the arc we're looking at of the angles POQ and PRQ. So what we say is that the angle POQ is actually twice the angle of PRQ. So we say that the angle POQ is equal to 2 times the angle PRQ. Okay, next, we're going to keep the angle PRQ, but we're going to get rid of POQ. And then we're going to create two new lines, S and T. So we get 3 triangles of the same type of make inside the circle. Again, they all share the arc PQ. These 3 angles, all of them that touch the circle, have the same angle. So we say that the angles PRQ, the angles PSQ, and the angles PTQ have the same angles. They are all equal to each other. Okay, let's do another one. Let us start at the origin of our circle, and let us draw a diameter. So, in order to do that, we start at point A, draw a line through the origin O to the point B. We then know that half the arc is half of the circle, and we know that the angle between A and B, if you were to think about it as an angle, it's a 180-degree angle. Next, what we're going to do is we're going to get the points C, D, and E, such that we have the angles ACB, ADB, and AEB. These angles, just like the ones before, are all going to be equal. However, these ones have a very special equality to them. Since the angle AB is 180 degrees, those are 2 out of 3 points on a triangle. 2 of the 3 points on the triangle are already being used up. And they're of a triangle, which is 180 degrees, their angle is 180 degrees. So to introduce that last point, that last part of a triangle, whether it's C, D, E, or any other point somewhere on that arc, the angle has to be half of 180 degrees. The angle will be 90 degrees for every single one of them. So I say that if you were to start at the origin and go to A, to then get to B, you would have to turn 180 degrees. So to get back to A from B, you would have to go in a triangle 180 degrees, with only 1 point left, meaning you have to do 90 degrees so that you can cut that 180 that you have already in half. So that from B to E and then E to A, you get 180 degrees canceled out. So it has to be an angle of 90. And we say that the angles ACB, ADB, AEB are all equal, and they're all equal to 90 degrees. Now let's make a very important note. This works because of the relationship between triangles and circles, which will get more intense as we keep going through grade 10, 11, 12, and into university. Welcome back from grade 7, 8, and 9. So let us first draw the picture so we can remind ourselves what we're doing. We have a straight line segment, L, which is carrying a uniform line charge lambda, and therefore there is some points above it which are experiencing electric fields, and we care about one point above one of the ends of our length. And we don't need to know the very length. We can just pick any point L long along this L wire in the x-hat direction. There's a point here. We are looking for the electric field. Okay, so what did we learn from grade 7? We learned about coordinates and their little quadrants and coordinates. So we learned that this wire could be spanned across an x equals positive and negative side. We're not going to do that because it's easier if then we say that we start at the origin 0, 0, and we move up. This is our z direction, x direction. We move up z amount. We move over x amount. And we have ourselves the coordinate points x0 and the coordinate point 0, z. Grade 8. What did we learn in grade 8? We learned about squares, and we learned about right triangles and the Pythagoras theorem, A, B, C. We learned that a squared plus b squared equals c squared. And we have here the length x squared. We have the height z squared. And we have the electric field line connecting them. We're going to, at this moment, call it r squared. What did we learn in grade 9? In grade 9, we learned how to take the square roots of these. So we have r squared equals x squared plus z squared. If we were to square root both sides, the square root and the square we know from grade 9 cancel and we just get r. These, because they are together, cannot be square rooted. So we keep the square root and we keep the squares. And we say, because this could be a negative or a positive, we say plus or minus. So r equals plus or minus the square root of x squared plus z squared. So that is all we can do from grade 7, 8, and 9. So let us return back to school and do grade 10, 11, and 12 pre-calculus, and then return back to this problem and see how much we can complete then. Hello class, and welcome to grade 10. Today we're going to do trigonometry. To do trigonometry, we need a triangle. Here we have triangle ABC. We are standing at angle A. Opposite A, we have the little a. Opposite capital B, we have little b. And opposite capital C, we have little c. So, what we're going to do here is we're going to stand at this angle, and we're going to ask about the things we can know while at this angle. One of them is, what is opposite this angle? The other is, what is adjacent to this angle? Last, we want to know what is the hypotenuse of this angle, which is really the hypotenuse of the whole triangle. In order to find what this angle is, we have three equations that can do it, so long as we know what the sides are. Say we know what the opposite and the hypotenuse are. We can use sine of this angle. Sine A is opposite over hypotenuse. Another way we can find this is if we have the adjacent side and the hypotenuse. We can use cosine A is the adjacent side over the hypotenuse. A third way to do this is with what we call tan A. The tan of this angle is the opposite side over the adjacent side. So these three equations, sine, cosine, and tan, will give us the trigonometry equations. Now, let's move on to something similar but slightly different. First, we're going to draw a line. We call this line the run. It goes on the x-axis, we call it the run. When we go up from here, we call this the rise. When we connect the rise and the run, the two lines there, we get what we call, in grade 3, do you remember what we called it? We called it a slide. Today, we're going to start calling it a slope. And the slope, we say, is the rise over the run. So we have the idea that what a slope is an amount of rise over an amount of run. But if we want to actually quantify that mathematically, we can turn these into symbols. So we say, from grade 6, we use our plot. Remember the grade 6 plot? We get an x-axis and a y-axis. And now our run is a difference of x. So we could say that the near point is x1 and the far point is x2. The bigger number minus the smaller number will get us that distance. So x2 minus x1. Next, we're going to do the same thing with y. We have the lower point being y1, the higher point being y2, and then we would have a difference between y2 and y1, which is going to be the rise. So the formula, then we get that the slope is equal to y2 minus y1 over x2 minus x1. And since we're using a bunch of letters instead of words, let's change slope to the letter M. Don't worry about why it's the letter M, it just is. So we get a point slope formula. We get the points x2, x1, y2, y1, and that will give us our slope M. Let's say that we don't know what the rise is. We know where we start, and we know what the slope is, but we want to know what y2 is. So we have to solve for y2. We want to know how much we rise. In order to do that, what we're going to do is we're going to move x2 minus x1 to the other side, multiply that by our known slope. We will then move the y1 to the other side. And we have here then a formula in terms of y2. So we can find what the rise is depending on what the run is. This gives us a formula. The formula y equals m times x minus x1 plus y1. If we assume we're moving off of an origin point, we can simply write y equals mx plus b. We can also write this in what is called the general form, which is ax plus by plus c equals 0. Okay, my grade 10 class, what we're going to talk about now is a system of linear equations. What does that mean? A system of linear equations means two or more linear equations. If we have two or more linear equations, what could we do with them? Say we have two. There are three cases that we can deal with. First, the case where the two lines intersect. There's one intersection point and there's one solution. By a solution, we mean where the two lines equal each other. Next, there's the possibility that the two lines never touch. They are parallel. In this case, we say there are 0 intersections, so there are 0 solutions. Solution, again, meaning where they touch, where they are equal to each other. And they are never touching, so there are no solutions. Third such case, two lines overlapping entirely forever. We would say that this has an infinite number of intersections, and therefore it has an infinite number of solutions. Hello class, and welcome to grade 11. Today, we're going to step in to our quadrant. Do you remember the quadrant? It goes 1, 2, 3, 4. Today, we are going to add our angles and triangles into our quadrants. So in order to start, we will draw an arrow from the origin down the x-axis. We will call this the initial arm. When we rotate it theta degrees, theta is a Greek symbol, a Greek letter. We use it as a symbol for degrees. So it is the number of degrees of angle of our initial arm. Where it stops, we draw another arm called the terminal arm. So we have our main angle, and we will also have an angle from the x-axis to the other side called a reference angle. So let us integrate trigonometry with our quadrant by moving this arrow around our quadrant. We're going to stop at a few locations. The first location is where it is when the degree is 0. There is no degree off of 0. So the theta equals 0. So that's the first case. Then we have 30 degrees, 45 degrees, 60 degrees, and then when we're standing straight up, 90 degrees. If we were to turn these into triangles, we would have at first 5 triangles. Let's go through them. Let's call it the flat triangle, the 30-degree triangle, the 45-degree triangle, the 60-degree triangle, which just so happens to actually be the same as the 30-degree triangle. And we have the standing up triangle, which happens to be the same as the flat triangle on its side, or standing upright, both of which are just straight lines. So we actually have just 3 cases: a straight line, a 30, 60, 90 triangle, and a 45, 45, 90 degree triangle. If you recall from grade 10 trigonometry, we had sine, cosine, and tan. So we're going to implement that into these 5 structures. So we have our flat line, our vertical line, our 30, 60, 90 triangle, and our 45, 45, 90 degree triangle. For the horizontal line, starting at our flat line, if we were to think about sine and cosine, the sine is the opposite over the hypotenuse. The hypotenuse we it's a flat line, we don't really know. But if we were to do Pythagoras' theorem, it would be 1 squared plus 0 squared. So that's 1 plus 0. So then it would be c squared equals 1. The square root of that would be 1. So therefore, the hypotenuse would have to be 1. So then we'd get, for sine, opposite, which is 0 height to the flat line, 0 over 1, which is 0. 0 divided by 1, 0. The cosine is the adjacent, which is 1 long, over the hypotenuse, 1. So we get that the cosine of 0 is 1. For the vertical line, we get the reverse, because sine is how high it is. And so the sine is 1 over 1, 1. And the cosine now is 0 long over 1 high. So now cosine of 90 is 0 degrees. Next, let's go over to the 45, 45, 90 degree triangle. If we assume the side lengths of this triangle are 1 and 1, then we get the square root of 2 is the hypotenuse. So we get the sine of 45 degrees is the opposite 1 over the hypotenuse, which is the square root of 2. 1 over the square root of 2. Typically, you don't want a square root in the denominator, so you times the top and the bottom of your fraction by a square root. And you end up with the square root of 2 over 2. So if you see the square root of 2 over 2, that's the same as 1 over the square root of 2. Next we have cosine, which is the adjacent side over the hypotenuse. The adjacent side is also 1, so it's also 1 over the square root of 2, or the square root of 2 over 2. Next we have the 30, 60, 90 triangle. We would say that its base is still 1, because that was our initial arm's length. This triangle here happens to have 60 degrees here. You can tell because the bigger angle will have the longer side. So the 30 is having 1, whereas the 60 is having the square root of 3. The adjacent side of this triangle, therefore, is 1, and the hypotenuse of it is 2. If we find what b squared is from the Pythagoras' theorem, we would find that c squared minus a squared. We'd find that the opposite side is the square root of 3. So the sine of 60 is the square root of 3 over 2. Cosine of 60 degrees then is adjacent 1 over the hypotenuse 2. Cosine of 60, 1 over 2. To go up to the top, we get the sine of 30, which is opposite 1 over 2. And the cosine would be the adjacent square root of 3 over 2. If we then want to find what the tan of these are, we can simply, we don't have to go through them again, we can just take the sines and the cosines and divide them. Tan theta is the same as sine theta over cosine theta. So for our flat line, we just put sine over top of cosine. 0 divided by 1. Tan of 0 is 0. Next, we have the vertical line. Sine over cosine would be 1 over 0. 1 divided by 0 is an undefined number. It's not a number. Can't do it. So we say undefined. So the tan of 90 degrees is undefined. Next we can do the tan of 60 degrees. Sine over cosine will get us actually just the square root of 3. Alternatively, tan of 30 degrees will get us 1 over the square root of 3. Since for the 45, 45, 90 degree triangle, the sine and the cosine are identical, then sine divided by cosine, tan of 45 degrees is equal to 1. So we just do kind of a quick recap / simplification of grade 10. In grade 10 trigonometry, we said sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. tan equals opposite over adjacent. We can just simplify this with our rise over run, which was now turned into x and y. Typically a line drawn as an arrow we call a ray, and since we drew all of this with a ray, we can call the line that will move through the x and y changes when it goes from 0 to 30 to 60. That ray, we call it r. So then we will get x, y, r. Therefore, now when we do trigonometry, we can simply say that the sine of theta is y over r, cosine theta is x over r, and tan theta is y over x. So what we're going to do next is find some laws of trigonometry. To do that, we will take this triangle right here. Triangle ABC. We will say, since we go opposites, the opposite of capital A is lowercase a. So the entire line from B to C will be A. So then the opposite of C will be C, and the opposite of B will be B. With this line, we have two right triangles. So we can create two different Pythagoras' theorems. One with this triangle and one with this triangle. So, what we're going to do is we're going to say that where the line cuts, we're going to put everything close to B. From B to that line was x. So, we have the whole line is A. This part is x, so what's left is A minus x. It's the amount of A that's left after we get rid of x. So, A minus x. So, first we set up by saying that the sine of B is the opposite h over the hypotenuse c. We will also then have that the opposite of c is h over b. So now we can solve for h for both of these equations. And we get that h is equal to c times sine b and b times sine c. Since they're both h, we can make them equal each other. So we can say that c sine b equals b sine c. If we flip them into turning them into fractions, we get that sine b over b is equal to sine c over c. And in fact, we can do this starting at any of the corners. So if we started at sine A and we were looking at sine B, it would be sine A over A is equal to sine B over B. And so on. We can do it for all of them. So what we get then, in fact, is the sine law. And it is sine A over A equals sine B over B equals sine C over C. Next, since we just did the sine law, let's do the cosine law. So we still have here our triangle, but we have labeled the point where the line touches BC as D. So we have two triangles, triangle ADB and triangle ADC. For triangle ADB, we have, let's do the cosine, we have the adjacent side, which we were calling x, over the hypotenuse c. So cosine b equals x over c. So if we solve for x, we get that x equals c cosine b. Let us take that x that we just found here so that we can stick it over here where the a minus x is. So we set this up by doing Pythagoras' theorem. We say that b squared is equal to h squared plus a minus x, all in brackets, squared. We know what x is, so let us first simplify this, and then we will stick in the answer to what x is and see what we get. So, first, in order to simplify this, we need to FOIL the a minus x. So a minus x squared means a minus x times a minus x. When we do this, what we get is that a squared minus 2ax plus x squared. And this is, of course, added on to our Pythagoras' theorem. So we get b squared equals h squared plus a squared minus 2ax plus x squared. Let us now rearrange this equation because we have something here. We have h squared plus x squared, which is actually the Pythagoras' theorem over on this side, h squared and x squared. What should that equal? It should equal c squared. So we can take that h squared minus x squared and stick it right there as c squared. So we actually get b squared equals c squared plus a squared minus 2a x, what was x? C cosine b. So if we plug this x back into the equation, we get then, finally, that b squared equals c squared plus a squared minus 2ac cosine b. This is the basic formula for what we call the cosine law. And we would say that the cosine law can be defined as c squared equals a squared plus b squared minus 2ab cosine c. Or we can say that the cosine of c is equal to a squared plus b squared minus c squared all divided by 2ab. Okay, grade 11, we're going to change it up a little bit. So far, we've been working with just straight lines. But what if we graphed something like this? This is what we call a quadratic function. So what we're going to do in order to understand this quadratic equation is we're going to follow along on our plot, and we're going to, in a t-table, plug in x and y values. So we're only really going to concern ourselves with the x values, because once you know the x value, you automatically will know the y value. So let us start at minus 2. X equals minus 2. When we go to minus 2, what we find is that the line is at y equals 4. So we put this in the t-table. At negative 2, we get plus 4 for the y. If we move our point along that line, we will then get to minus 1. At minus 1, we get y equals positive 1. When we move the line to 0, we get y is 0. When we move over one more time and we get x equals 1, we get y equals 1. And when x equals 2, we get y equals positive 4. If we were to keep going, we get at x equals 3, y equals 9. This gives us the simplest form of the quadratic function. That is when y equals x squared. So if you were to square all of these numbers, negative 2 squared, positive 4. Negative 1 squared, positive 1. 0 squared, 0. 1 squared, 1. 2 squared, 4. 3 squared, 9. So you could keep going. 4 squared, 16. You would know instantly then, using that formula, if you plug in an x, what the y should be. And that is what we call a quadratic function. The standard quadratic form is y equals ax squared plus bx plus c, where a does not equal 0. One of the things that's very interesting to do with this level of mathematics is what we call completing the square. So the way this works is we will typically be given some sort of quadratic function, a times x squared plus b times x plus c, where this doesn't make a complete square. So what we want to do is complete the square. First, let's simplify by getting rid of the a by dividing it from the ax squared, and let's divide it from the bx and the c. What we end up with then is a formula which says x squared plus b over a times x plus c over a. What is x squared? Anything squared is a square. So we would say it is a square that is x long and x high, x squared. Okay, next we have b over a times x. What is a square? Or what is a rectangle? It's the base times the height. We said x is a base and it's a height. We could say b over a can be some number. So then let's actually cut it in half. So let's take a rectangle that we call b over a times x. And what we're going to do is we're going to cut it in half. So we get b over 2a times x and b over 2a times x. In doing this, we can take this and move it over onto our square, and we get almost a new square. But it's missing the corner piece, which is why this is called completing the square. So ideally, we want kind of the c over a to fill that square. But if it doesn't, that's what we're doing. We need to find that completed square. So that last little square will be the base of b over 2a, and it will be the height of b over 2a. So the square itself will be b over 2a times b over 2a. So it'll be b squared over 4a squared. Since we are just adding that square into this space, we need to add it into the formula and remove it from the formula at the same time. We will rearrange all of that so we have a square, and then when we're done and we've solved it, we remove it again so that we actually know the full amount and not the amount plus our imaginary completed square. So we add it in and we subtract it back out. So we talk about how this is a square now. So we separate the equation so that we turn this whole thing into a square that has the same base, which will be x plus b over 2a times x plus b over 2a. So we can rewrite this formula as x plus b over 2a squared plus c over a minus b squared over 4a squared. What we want to do, really, ultimately, this whole point, was we're trying to find what x is. Trying to solve for x. In order to solve for x, we will set the equation to 0. So we get that a plus b over 2a squared, there's two of them for that square, plus the c over a that's kind of just hanging out, minus the b squared over 4a squared that we need to get rid of again, equals 0. So in order to solve for x, what we're going to do is we're going to take all of the non-x values and we're going to move them to the other side. Now let's just simplify this by setting the denominator to be the same. To do that, we're going to have to multiply the numerator of c by some value in order to make this work out. When we do that, we get that b squared over 4a squared minus 4ac over 4a squared. So our denominators are the same, so we will be able to mix them together. Next, we can also see that we have in the x side, the x is in a bracket which is being squared. So let's square root this side so we can square root the other side and get that x by itself. Now that x is outside of the bracket, we can move the b over 2a to the other side. So what we get is the quadratic formula for solving for x. You've probably seen this before. X equals minus b from that b over 2a. It was positive, so when we put it to the side, it becomes negative. Negative b. Then we have the square root value, so we have to incorporate square rootedness, which is like that negative 2 became 4 and positive 2 became 4. Well, a square root of 4 then could be negative 2 or positive 2. So we have to say that x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. In order to try to wrap up grade 11, we need to talk about functions. So we've mentioned two of them. That was the linear function and the quadratic function. So the linear function was y equals x, or some value times x plus some value. That was our slope. It's just a straight line. We've also now talked about how we could have quadratic functions, like y equals x squared. Both of these we can write as a function. To write it as a function, we literally write f to stand for function, and then the value we care about changing, in this case, x. So we say that y is equal to the function with respect to x. So that when we put in -2 as our x, what did we get? We got the result of the function, which was that point on the slope. Somewhere on that line is a number. That's the function. And that line happens to be on our grid, which has a y value. So that at that same point, when x was -2, the function was at the same value as y. So y equals the function with respect to x. So we write y equals f of x. Or we can write y equals x, or we can write f of x equals x. That's our linear function. The quadratic was that x squared. We also talked about things like trigonometry, where we have things like tan theta. Tan theta is sine theta over cosine theta. Sine and cosine theta are both functions. So this means that we could have functions in the numerator and denominator. We call these rational functions. That is, we could say that h of x is equal to f of x over g of x. It's a function which is made up of a function divided by a function. We also have absolute functions, which is when we don't want a negative number for some reason, we can put these vertical bars, and it will turn something like when y equals x, and it goes into the negative, it turns that negative into a positive. And so we get a different looking graph. So it's because it's a different function. It's the absolute function. We can also, since we have this absolute function, which can take a value that used to be negative, turn it positive, since it can be split up into positive a if a is positive and negative a if a is negative, we can do something similar with what we call a piecewise function. Piecewise functions are functions that can be split, that once you reach a certain point in your function, it changes. Now, if you have trouble understanding something like a piecewise function, you could think in terms of like a video game, where after a certain level of experience, there's a certain level of the curve difficulty. So that while you're playing the game, you get up to maybe level 3, and it has you kind of on a simple learning curve. But once you reach that level 4, the game ramps up, and maybe it does so almost exponentially. So you could have some sort of function in a video game where the learning curve is very slow, and then once all of the skills are learned, it ramps right up. So you would take that function, it'd be easier to take a function and split it in half and say this half is linear, this half is quadratic. And therefore, you could have a function which you call piecewise. You could essentially say then that while x is below this value, or that y is under this value, that we have the function f of x. And after that point, you could say that we have the function g of x. And that they're the same function, it just, once it reaches that point, it'd be easier to graph it with a different type of function. So that's what we call piecewise. Last one that we're going to talk about is the reciprocal function. Y equals 1 over the function, right? Since we had the rational function, h of x can be equal to f of x over g of x. What if the function f of x is equal to the function 1? That would give us a reciprocal where our h of x, which we're going to plot with y, so we say y equals 1 over that function. So we get reciprocals. Okay, let's just wrap this up by going back to our system of linear equations. When we had the systems of linear equations in grade 10, we were talking about just linear lines. So when we had two lines that crossed each other, two lines that were parallel, and two lines that were overlapping. Now that we've introduced quadratic functions, let us talk about what happens when we have a quadratic and a line. We will do that on the top. And when we have two quadratics, and I'll do that on the bottom. So in the first case, we have both the linear and the quadratic. If there are 0 intersections, there are 0 solutions. A solution again being where the two functions, the two lines, are equal. Where they are equal is where they are the same y, which is where they are the same point on the graph. So no intersection, no solution. We could also have the case where the line touches the quadratic at one point, like a tangent. And the same for two quadratics. They just touch at one single point. That would be one intersection, one solution. And finally, obviously, we could have it such that the line cuts through the quadratic, or the quadratics intersect each other in 2 points. So we would get two intersections, therefore we would get two solutions. We of course can also have the linear line, which at a certain point is just stuck on top of the other line, or we could have two quadratics that are stuck on top of each other. But for the most part, these are going to be these cases that we deal with. Hello class, and welcome to grade 12 pre-calculus. In grade 11, we learned all about functions. Now we want to learn how to move the functions around. So, just like in grade 5, when we took the triangle ABC and we learned how we could move it and we learned how we could rotate it, that's what we're going to do, not just with shapes like triangles anymore, but with functions. So taking a linear line and making it stretch out longer, go further, or turn faster, or pick it up and put it somewhere else, or rotate it. These are things that we want to be able to do with functions. In order to move a function, let's go back to thinking about triangles. When we had the triangle, we had the slope equals the rise over the run. So we also then turn that eventually into y equals mx plus b. B was the y-intercept. It's where the function of that linear line will touch the y-axis. And we could set it such that it touches it at 0. And we could make the slope equal to 1, in which case our y equals mx plus b simply becomes y equals x, the most basic linear equation. So if we think about that, the m times the x, that m is what moves the line up and down. It's what makes it rotate, essentially. It changes the slope, so it changes the rotation. The b caused it to move up or down the y-axis, because it's going to be x going through 0. So if you said y equals x plus 1, that's the exact same line shifted 1. So that b at 1 moved us up 1. So the b is moving the line. It's transforming the line, is what we say. So we have the function x, right? A linear line, y equals x, is a function. It's the linear function. So y equals mx plus b is the function x being transformed in two ways. It's being rotated, and it's being rotated or scaled. So we're going to change the rotation because we're not attached to anything. We're not a shape anymore. So we're going to call it scaling. And it will scale in two ways. You can scale x and you can scale y. So let us assume that the m is some sort of scaling function, and you can see it in this case where 1/2 of x versus 2 times x are moving them up the y-axis faster or slower or faster. So if we remove the function x and we replace it with the symbol for a function f of x, we would have that y equals m times f of x plus b. So what that would do is the m would scale y and the b would move that function up or down y. What we want to be able to do is also scale along x. To do that, we put the scaling differences inside the function. So in total, what we get is y equals a, so the a is our m, y equals a times the function plus k. And in the function, we have b times x plus h. K just moves us up or down. H just moves us left or right. X is the number that we change. It's our independent variable. That's what we call it. B scales us in the x direction, and A scales us in the y direction. Okay, class, next is a very important type of function. So, we were introduced in grade 11 to reciprocal functions. That is a function which is 1 over a function. This is not a reciprocal. Understand that. So this is an inverse function. So what we tend to write is y equals the function f to the power of -1 of x. Now typically when you're using a number and you say 2 to the power of -1, so you could write that as 1 over x. When that -1 is attached to the function, it is not a power in the same way. It's not an exponent like that. This is the symbol for an inverse function. And an inverse function has a certain type of property. So first let's do a picture to get an understanding. We have here our quadratic plot, and let's just do the simple y equals x line through it, and then let's draw a function which comes right up to that y equals x line, but it does not touch it. The inverse function of this graph is the mirrored version along the y equals x line. Inverse functions are typically along this line unless something has been transformed. So our inverse function will look something like this. To get an understanding of inverse functions, what we will do is deal with what is called set theory. Set theory is quite simple. It's just dealing with things essentially in bags. So what we're going to do is think about when we have our plot is x and it is y. Now, when we want to find some number, we just have to look along the x. Any number along the x is a number that we can pick. If we stop imagining all the numbers on the number line as being numbers on a number line, and instead we take all those numbers and we put them into a bag. A bag we call the set of x. Another way we call it is the domain of the function. That is all of the numbers that you can plug in for x. So let's just draw a little set, a little oval, which represents a bag holding all of the x values. A function, the purpose of a function is to take objects out of the domain x, to take them out of this bag, operate on them. That's what f of x does. It takes a number and it does something to it, and the result of that doing something to it gets you the result y. So you put it into the set y. The inverse function is if you were to take one of the values from y as if it was the same as a domain, and you plug it into the inverse function. The inverse function operates in the inverse way than the function does, so it will then create a number which is identical to the domain value of x. So an inverse function will undo the work of a function. A reciprocal function will not do this. Only the inverse. That's why they're different things. So let's do an example. F of x equals 2x minus 3. So let us create a t-table. And in this t-table, we will have x, f of x, and the inverse function. So in order to understand this, I have just plugged in a bunch of numbers that will get us some understanding of this. So what we will do is we will take a value from our domain. Let's take -7, and let's do the function to it. 2x minus 3, that's 2 times -7, -14, minus 3, -17. So we take the -7, we act on it with the function, and we get a -17 in the y. If we take -17 and we plug it into our inverse function, which we don't know what it is yet, we take that -17 and we plug it into the inverse, we get the answer -2. And we put it back into our domain, -2. Let us then take -5 from the domain, operate on it. -5 times 2, -10, minus 3, -13. We put -13 into the range y. We pick that -13 back up and pretend it's an x and plug it into the inverse function. -13 in the inverse function gets us the result -1. Now let's go -2. -2 times 2, we get -4, minus 3, -7. So we plug -7 into here. If we put -7 into our inverse, we get a half. Keep going. Take -1 out of the domain, act on it with the function, and we get -5. Act on -5 with the inverse function, and we get +1. So then, if we actually take these values and we try to figure out what the inverse is, we can actually find that the inverse is x plus 3 over 2. So anything that we take out of y, we plug into that x, and we plus 3 over 2, and that's how we get all of these results. So what we should find from our table then is if we were taking values from x, plugging them into y, and then those get us back to the x when we do the inverse, we will find values like the -2 gets turned into -7. -7 then should bring us back to -2. And we can see that it does. -7 as the domain with the inverse function gets us back out to -2. It's also the case when we took the 1 and we operated on it, we got -1. When we take -1 and we operated in the inverse, we got back out 1. It brings us right back to x. All right, my grade 12 pre-calculus class, let's talk about radians. A radian is a special type of measure. A radian is what happens when the radius and the arc are the same value. So the angle is 1, the radius is r, the other radius is r, and the arc that connects them to finish off that sector, the angle, the arc size is also r. This is what we define as a radian. If you convert a radian into degrees, 1 radian is approximately 57.29578 degrees. And we could say, let's just approximate, pi is approximately 3. If we go through our main values, we could say that 30 degrees is the same as pi over 6 radians. 45 degrees is the same as pi over 4 radians. 60 degrees is the same as pi over 3 radians. 90 degrees is the same as pi over 2 radians. 180 degrees is the same as pi, and a full circle is 2 pi. So, we take this information and we draw ourselves a quadrant. And we draw ourselves a circle in that quadrant whose center is at the origin. And we make this circle 1 radian long. 1 radius. R equals 1 all the way around. This is what we call a unit circle. We can see here that where the circle touches the x-axis, we stopped at the point 1. That's 1 radian. And it's how high? 0 high. So it is at the point 1, 0. Coincidentally, not really a coincidence, it's actually how this works, the cosine and sine are of those values. So then we get at the 30 degree mark the values of 1/2 and the square root of 3 over 2. So at 45 degrees, we get our sines and cosines again, the square root of 2 over 2 and the square root of 2 over 2. At 60, we get the square root of 3 over 2 and 1/2. And at 90, we get 0 and 1. Okay, so in order to finish off this trigonometry, let us also introduce the reverse functions of these. If we have the sine is opposite over adjacent, or y over x, we have the reciprocal of sine, which we call the cosecant. Cosecant theta is 1 over sine, so it's the radius over y. The inverse of cosine, 1 over cosine, is secant theta, and that gets us r over x. And the inverse of tan, 1 over tan, is cotan, and that is then x over y. Let us continue on with trigonometry and functions. So, what we're going to do is, instead of doing the quadrant with a unit circle, let's do sine and cosine and tan with a plot. So what we're going to do is we're going to go between -1 and 1 on our y-axis and just get a long x. If we were to follow the circle around and get ourselves sine, the sine function will look like this. The cosine function is shifted over by pi, and so it will start at 1 and do the complete same pattern, but just shift it over. So in order to get some understanding of this, let's put the unit circle next to the plot. So we start at 0. So for sine, the answer is 0. If we move up to 90 degrees, sine of 90 is 1. So our plot, the point gets up to 1. If we keep going back down to 180, we reach 0. If we keep going then, we will get -1. And then, since it's a circle, we get back to the start, which happens to be back at 0. Cosine is the same basic principle. So it's shifted over, and so it's shifted over by 90 degrees, so we start at the top. So since we start at the top, that's starting at +1. So then it goes to 0, then -1, then 0. And then finally, back all the way up to the top, +1. Now, we introduce tan theta. We know that tan theta is sine theta over cosine theta. And we also know that there are points which are 1 divided by 0, which is impossible. We can see it on our plot. Every time cosine is 0, every time it's touching the x-axis, there is nothing that we can do for tan. And so what we do is we draw vertical lines called asymptotes. So these two lines are asymptotes, and our function cannot touch them. So the tan function, when you plot it, looks like this. If we were to follow along with the unit circle, at the start we get 0 and 0. But as tan moves up to 90 degrees, it flies off the chart. And as you go from the +1 on the unit circle back down to the 0, it pops up from the bottom and meets back up to 0. And then it just repeats this pattern as it goes. Let us wrap up trigonometry in the unit circle by putting them all together on a single plot. So we have our circle. Let's draw a radius, and then let's draw a line that goes up to that radius. That will get us the line sine. If we draw a line horizontal, that is our cosine. We can rearrange this into a triangle, in which case we get the triangle cosine plus sine equals 1. Next, if we make a tangent line from that point down to the x-axis, that line there is tan. And the line from where tan touches the x-axis back to the origin, that line is actually secant. Since the tan is a tangent, that means where it touches that point R, that angle is actually 90 degrees. So we find ourselves getting another right angle triangle. This one being tan squared plus 1 squared, so 1 is squared is 1. So tan squared plus 1 equals secant squared. Next, if we go from the tangent up to the y line, the y-axis, that is the cotan. And the line from the origin to cotan is the cosecant. So therefore, we get another right triangle. This one being that cosecant squared equals cotan squared plus 1. So these are 3 trigonomic identities. Next identity. In order to find this one, what we're going to do is draw a triangle. Triangle RST. Okay, so triangle RST has the angle, let's call it B. Let's make the hypotenuse R, R being 1 from our unit circle. So sine is opposite over hypotenuse, so sine of B over 1, so the opposite side then has to be sine B. The same is true then for the cosine. The adjacent over 1, cosine B over 1, cosine B. So the adjacent side is cosine B, the opposite side is sine B. Next, what we're going to do is draw a rectangle around this triangle so that the points of the triangle touch the rectangle. This then gets us 3 extra triangles. And we will make the rectangle RUVW. Since it's a rectangle, we know that all of the corners are 90 degrees, so we know that all of the triangles are right angle triangles. Let us label the bottom base to that triangle's first line. Let's label that angle A. So what we're going to do is try to solve for the opposite and adjacent side. So to do that, we say sine of A is opposite over hypotenuse. So opposite is hypotenuse times sine A. So then the opposite would be sine A times cosine B. And the adjacent side then would be cosine A cosine B. Let us solve for the top triangle. So we know that if we went from here all the way around, we would have a few angles to cut through. One of them being 90 degrees from our right angle from that triangle. If we do a little bit of math, what we will actually find is that this angle here is the angle A. So its hypotenuse side is the sine B side. So when we do the opposite equals sine times the hypotenuse, the opposite will be sine A sine B. And for the adjacent side, for the cosine side, we will get cosine A sine B. So we're starting to fill out all of these sides. So now let's work on the far triangle. What we can do is try to find the angle A and B together. So if we were to have a flat line here, the angle that connects those two comes up to the rectangle and then goes parallel again. There is an identity with angles that we can do, that this angle here should be equal to this angle here. It's canceling out that 180 degrees. It's like you had to go here, you reached that point, you did 180 degrees to keep going, but you didn't, you went up, and then you went back. So it cancels the 180 degrees, so the angle on one side is equal to the angle on the opposite side. So if this is the angle A and B, then this is the angle A plus B. So the opposite side of this angle will have to be then sine A plus B. And the adjacent side, the cosine side, will be cosine A plus B. Here we get our identity, because we can see that on this side of the rectangle, the length is the length of sine of A plus B altogether. And that side is obviously equal to the other side of the rectangle, which is the combination of cosine A sine B and sine A cosine B. So we get, therefore, that the identity of sine A plus B equals cosine A sine B plus sine A cosine B. In the exact same way, on the bottom we have cosine A cosine B, sine A sine B, and cosine A plus B. So if we just want that space cosine A plus B, we can see that it will be cosine A cosine B minus sine A sine B. Next is what happens when we subtract the angles. So let's take the same triangle rectangle combination, but let's turn it on its side. So we have the triangle RST inside of the rectangle RUVW. The hypotenuse is 1. The angle for B then will be sine B, cosine B, hypotenuse 1. If we were to say that the angle between the cosine B line and the rectangle's base is A, and we're also saying that the triangle is the angle B, then the angle that's left is the angle A minus B. So then the opposite over the hypotenuse is 1, so the opposite will be sine A minus B. And the adjacent side will be cosine A minus B. So if we work our way around the rectangle again, we find that this angle is A, so we get sine A cosine B, because its hypotenuse was cosine B. And the adjacent side will be cosine A cosine B. Likewise, the last rectangle over here, we will get the angle of A over here. So we will find that its opposite is sine A, but its hypotenuse is sine B, so sine A sine B, cosine A sine B. So we get the exact same principle as last time, where we're measuring the lengths of the rectangle. So we can see that we have the sine A minus B, that's the small section. So it's going to have to be the entirety of this line, which is sine A cosine B, minus the remainder, which is minus cosine A sine B. And then we also have the whole bottom, cosine A minus B, which will be made up of the two values on the top. So cosine A minus B equals cosine A cosine B plus sine A sine B. Last one, the double angle identity. So we start out with some triangle of angle A. And we say then, with its hypotenuse being 1, opposite sine A, cosine A, 1. Familiar with this? We add on another triangle of identical make so that it's a double angle, AA. We know that the area of a triangle is 1/2 the base times the height. Our base in this case, is 2 sine A's. The height will be the line that was our adjacent side, cosine A. So the area will be 1/2 times 2 sine A cosine A. So the half and the 2 cancel, and the area is just sine A times cosine A. Let us rotate this triangle and find a new height. So what we're going to do is say that the angle of the 2 A's is now the angle 2A. And the opposite side will be the height, which we will call, in the case since our hypotenuse is 1, opposite will be the sine of 2A. So what we should get is a new area formula, right? It'd be the new base and new height times a half. So the area equals 1/2 times 1 times sine 2A. However, just because the formula is different, the area shouldn't be. We didn't make the area bigger or smaller, we just turned the triangle on its side. So we know that these two areas should equal each other. So therefore we get sine 2A over 2 is equal to sine A cosine A. If we just solve for sine of 2A, then we get 2 times sine A cosine A. And that is our identity. Let us finish off grade 12 pre-calculus with some new functions. Here is the exponential function. The exponential function is a number, let's say approximately 2, to the power of x. An exponential function is a function which, as x increases, the value gets larger and larger and larger, faster and faster, and it almost starts shooting up in a straight line. What is the opposite of growing exponentially? The answer is not to decay exponentially. That would just be taking the e to the x and flipping it. No, the actual opposite way, the inverse function of e to the x, is what we call the natural log. If e to the x grows exponentially, which means as it grows, but it grows faster and faster, the inverse isn't to decay. The inverse is to grow as you grow, but to grow slower and slower. So as the x increases, the natural log of x keeps growing, but it does so slower and slower. Whereas e to the x, as x grows, it grows faster and faster. That's what makes those two opposites. Finally, in order to wrap up pre-calculus, we need to talk about function operations. So we know that we can move a function around our grid space. And we also know from our rational functions that we can say that a function can be a function divided by a function. Since we can do that kind of math, why not the other types of math? So that's what function operations are. Take a function, assume it's kind of like a number, and then do number math to it. So we get addition and subtraction. We could say h of x equals f of x plus or minus g of x. So we could also write that the h could be written as f plus g. So we could say f plus g of x. We can multiply. H of x is f of x times g of x. We already know the rational h of x equals f of x over g of x, where g of x does not equal 0. And finally, there is what we call a composite function, which is when you take a function as a number and you then plug it in as the variable into another function. So you could say that the h of x, the function of h with respect to x, is equal to f with respect to g of x. So another way of saying this is that the h is the function composite f composite g of x. Welcome back to the problem. So first, what we got to do every single time, we got to draw the problem. We actually know from grade 4 about similar triangles. If this corner and this corner are the same angle, and this angle and this angle are the same, and they are. It's the same line and 90 degrees. How could the same line and 90 degrees be any different of an angle? Same argument, this line and 90 degrees this way. So this angle and this angle have to be the same. So let us call this triangle, let's just call it triangle EX, EZ, E is similar to, let's call this triangle, I'm going to change the R to a curly R, a cursive R. I'm going to call it curly R. And it's similar to X, Z, curly R. So therefore, we could say, let's call this angle here theta. It is a Greek letter. So then this one is also theta. So let's get into what we learned in grade 10, which is trigonometry. So we got ourselves our theta for trigonometry. We learned in grade 10 sine theta is equal to the opposite of the angle, x, over the hypotenuse, curly r. And we have a second one actually over here. The sine theta is also e to the x in this triangle over e. We also learned cosine theta. Cosine theta is the adjacent side over the hypotenuse. So that's z over curly r. And the cosine theta for this triangle up here should be then the adjacent side, e to the x, or e to the z, sorry, over e. So we have two sets of problems going on. Let's do this one over here and this one just over here. Let us solve this one for x. X equals. So in order to do that, we have to get rid of the curly r. To do that, we times it by r. And what we do to one side, we have to do to the other. So then these r's cancel, and we get curly r sine theta. Same for the cosine. We should get z equals curly r times cosine theta. And the same thing over here. The e's will go over here. So we get e to the x equals e sine theta, and ez equals e cosine theta. We also know, let's just do it to this one here, tan theta. Tan theta is the opposite side, x, over the adjacent side. Okay, so what did we learn in grade 11? In grade 11, we learned about different types of functions. One function we learned about was the absolute value function. So I want to know the absolute value of r, because r has to be something real. It can't be a negative thing. This can't extend a negative distance. It can go in the opposite direction, and if that were to be called negative, negative would just mean pointing south. I want then the magnitude, the length of a line, which is always positive. So we want the absolute value function. Now, the absolute value function happens to be the square root of x squared plus z squared in this case. So we are already set here. We can also then do e, which is the square root of ex squared plus ez squared. What did we learn in grade 12? One thing we learned in grade 12 were the opposites of these values, such as, let's just do one of them, secant theta. Secant theta was 1 over cosine theta. Another thing we learned in grade 12 were identities. One such identity is sine squared theta plus cosine squared theta equals 1. If we divide this whole thing by cosine squared, we would get sine squared over cosine squared, which would give us tan squared theta, plus cosine over cosine would give us 1, and 1 over cosine squared would give us secant squared theta. So these were two identities we learned in grade 12. So then this is all we can do in order to solve the problem using grade 10, 11, and 12. We're going to have to learn calculus to solve this problem. So let us just do years 1 and 2 of calculus and see if we can finally solve this problem. Hello class, and welcome to grade 12, or first year university calculus. Calculus is its own type of mathematics. It's the mathematics of change, about making small changes in one thing to see how it affects the rates of change of other things. So, in order to do that, we want to find a way to talk about, in mathematical form, the idea of approaching something a little by little until you reach your goal. And that is our limit function. We call it the limit function because typically it tells us the limit at which that function might break. For example, the tan function, the tan was sine over cosine. So anytime cosine was 0, it would be 1 divided by 0, which is undefined. So it doesn't show up on a plot. So as x approaches that asymptote that we had to draw for tan, what is the value of tan of x when x is on the asymptote? There, it's undefined. So that's the limit. But what if we want to still put a number there, just in order to fill in a blank space, because we know it's going to repeat also near that line, but in the bottom coordinates, and then it will come up and still fill up the rest of the graph. So why not just say it is that point? And that is what calculus does. So we have this limit function, or the limit of a function. The limit as that x approaches a, say in this case, let's call the a asymptote. So the limit as that x approaches the asymptote of the function with respect to x, so in this case tan of x, equals L, the limit of the function, which in this case for tan would be an asymptote. We can make the values of f of x sufficiently close to L, enough to say that, let's say that it is L, and we do so by bringing x as close to, but not equal to, a. And that's what we write as the definition, in a sense, of what this limit is. Now that we've got ourselves an introduction to calculus, let us go back to our triangles and circles. So, one of the most important things that we had learned from triangles and circles were tangents and slopes. Tangents being a type of slope. Slopes being this rise over run. So, rise being the y value of a graph, and the run being the x value of a graph. Calculus has these too, right? Because all calculus is doing is saying, taking those graphs that we've learned about all through these years, what if we just step through one at a time, very slowly, and see what the rate of change is? That's what calculus is all about, rate of change. In order to find the slope in calculus, what we talk about are derivatives, and in that case, we write this little comma above our function to indicate that we want the slope of that function. So if we have the function f of a, so in this case we're talking about some definitive value that we know, f of some number, really. So we want to get into slopes in calculus. In order to do that, we do derivatives. A derivative is just a fancy way of talking about slopes. And in order to do that, we take our function, like f of a, and we put a comma right next to the f to indicate that we're doing the derivative of f of a, which is just the change of y, the rise. So that is f of a plus h minus f of a. So both of them went f of a, but this second one went a little bit further. So that's the second value. It's higher than the other value. So this number minus this number, so that's the rise, right? Divide by the run. So it's just a slope. But we don't want to touch 0 because we made our denominator, our run, come to equal 0 if we touch it. And then we'd have a function, which is a fraction, dividing by 0, which is not good. So the limit, as h approaches 0, the limit tells us that h is going to get as close to 0 as possible, but not touch it. And as a result, the function's slope, the answer will get as sufficiently close to the number we want, the value that it actually, say, is at that moment, and will give us our answer. And that's what calculus is all about. Another way that we could write this is the limit as just x approaches a of the function f of x minus f of a, divide by x minus a. Still, it's the same idea. This is the rise. The f of x value is what y would equal in your function, in your equations. Y equals f of a as well. So it's y2 minus y1 over an x2 minus x1. Both x and a are x values. So rise over run. Both are functionally the same thing. We also typically write an f of x value, and we kind of distinguish between these two values. One is for a more definitive answer, one where we know the value of a that we're looking for. The x is typically one where we're just kind of thinking about the variables. Historically, the reason that calculus was even invented was both for understanding physics and understanding the rules of gambling so we could tax them better. And so there were people all over the world trying to solve how to do these rate of change problems. There are two people credited with the invention or discovery of calculus, one being Leibniz and the other being Newton. So there are two forms of calculus. They're the same mathematics, but the notation is different because they were invented by two different people. And so sometimes you will see the f of x, f prime x notation, And sometimes you will see a dy over dx version. The dy over dx equals f prime of x. It's the same notation. And we can say if y equals f of x, then dy over dx would actually just be d over dx, the derivative of y, equals the derivative of the function. So we can see that they're the same thing. But you will see two different notations. Don't be confused by that. It was invented by two different people. Now let's talk about circles in calculus. Circles in calculus, we would use the equation of a circle. X squared plus y squared equals r squared. If we talk about the unit circle, we can make that radius 1. 1 squared is 1, so we get the equation x squared plus y squared equals 1. That's the equation of a unit circle. Now we have a rule in calculus. It's called the vertical line test. If you can put a vertical line through your function and it touches two y points on a single vertical line, it's not a function. So we have to divide a circle in half because it fails the vertical line test all the time. So we have to get a top arc and a bottom arc. Since we're trying to solve for y, let's solve for y, and we could see that because we're going to take the square root, we can see the two functions. Y equals plus or minus the square root of 1 minus x squared. So we get the two functions, and we can divide them up into f of x, which is plus square root of 1 minus x squared, and g of x equals the negative square root of 1 minus x squared. Let's do the dy over dx formulation for the equation of a circle. So the derivative with respect to the change of x, so d over dx, of the function x squared plus y squared equals, and what we do to one side, we have to do to the other, so then that is the derivative with the change of x of 1. Okay. We can move the derivative symbol inside of the brackets just like we would distribute any number. In which case then we would get the derivative with respect to x of x squared plus the derivative with respect to x of y squared equals, and we just did it for the derivative with respect to x of 1 equals 0. Why? Because the derivative with respect to x is asking, as x changes, how much does the number or the function change? In this case, how much does the number 1 change as x changes? And it doesn't. It will always be 1 all the way forever. That's what it would just be, a straight line at 1, at y equals 1. So, what is the derivative of x squared though? X squared is, in fact, some value. It has a slope, and its slope is 2x. The derivative with respect to x of y squared is not really something that we get. But we could break it up such that we get that the derivative with respect to y gets us y squared times dy over dx. What is the derivative with respect to y of y squared? It's 2y. So we get x squared plus 2y dy over dx equals 0. We can rearrange this and get dy over dx, our slope, and it equals negative 2x over 2y. So the 2's cancel, and we get negative x over y. So that would be the derivative of a circle, or ultimately, that would be the slopes of a circle. Now that we know about how to do derivatives, let's talk about higher level derivatives. If y equals f of x, then f double prime of x would be the derivative of that derivative. So it would be that y double prime could be written as d squared y over dx squared. That's the notation that we tend to write. For the time being, double prime will be as high as we go. So let's move on now to trigonometry in calculus. What is the derivative of sine x? The answer is, surprisingly, not really surprising because they're talking about a circle, cosine x. What is the derivative of cosine x? It's actually negative sine x. What is the derivative of tan x? It's secant squared x. And what is the derivative of cosecant? It is negative cosecant x cotan x. What is the derivative of secant x? It is secant x tan x. We can see the secant and the cosecant have a similar system going on here, where one has the tan, the other has the cotan. One has a secant, one has a cosecant. One's positive, one's negative. And last, to do the opposite of tan, what is the derivative of cotan? It is negative cosecant squared. And we can again see a pattern between tan and cotan having a secant or a cosecant. So the tan having not the co, and the cotan having the cosecant. Now, let us talk about a very interesting function. What is the derivative of an exponential function? An exponential function is a function whose slope is increasing exponentially, so that at every point of its graph, the slope is an exponential type slope. That's what makes something exponential. Its slope is exponential. And so the derivative, the slope of an exponential function like e to the x, is e to the x. It is its own slope. In the reverse, what is the rate of change of log? The thing that grows forever, but does so slower and slower over time. It is 1 over x. Now, everything that we've done has always had some sort of opposite. We learn addition, we get subtraction. We learn multiplication, we get division. We learn exponentials, we get logarithms. We learn sines, cosines, tans, cotans. We get a lot of opposites. We have here derivatives, so we have to have some sort of opposite. We call them antiderivatives. And we get a function, capital F, is called an antiderivative of lowercase f on an interval I, so like a line, if capital F prime x, so the derivative of the capital F function with respect to x, is equal to our f of x, or lowercase f of x, for all of the x values in that interval, within that line. If capital F is an antiderivative of f on that interval I, then the most general antiderivative of f on I is f of x plus c, where c is some arbitrary constant and f of x is the particular antiderivative of f of x. So the plus c is because when we take a derivative of some number, if we have a function plus a number, and we take a derivative, we will end up with the derivative of a function plus the derivative of a number, which is always 0. So you don't know if you've lost the number, so you add it back in, plus c. And that c might equal 0, and you get rid of it again. But for safety's sake, you put the c there, because you don't know if you're going to lose a number. Let us think for a moment about this antiderivative. Well, first, let's think actually about the derivative. So, what is a derivative? A derivative is a slope. A slope of what? Of a function. What's a function? A function, we could just think about, in the most simplest terms, is some sort of squiggly line on a graph. So we have a squiggly line on a graph, and it squiggles around, say like sine. We know sine of x literally wiggles around the x equals 0, or the y equals 0 line, and it goes up and down x, moving all the way into infinity. And it wiggles back and forth, and so it's got a slope that changes over time. We learned that that slope is apparently cosine, but it's just this function, and it wiggles. And so the derivative is when we stop the wiggle at a point, and we say, at this point, which direction is the line moving? Are we starting to wiggle back down? Are we still moving up? Are we moving left, right, up, down, into the page, out of the page? Which way are we wiggling? That's what the function, the slope, the derivative is asking. At that point, which way are we moving? Right? So the derivative is always asking, which way are we moving? So what is the antiderivative asking? Well, it's taking a bunch of slopes, essentially, and saying, where is the line? Where is the line? Or what is the function? What is the function? The function, in one of the cases that we went through, was a circle. And one of the things that we need to know when it comes to circles, which is the whole reason we're doing this in the first place, is to find what the area of a circle is. By finding that function in the first place, we were finding that boundary that the area was in. So now we want to find area of circles using the small amount of change that we've invented. This was the point, to find the area of circles. Because once we find the area of circles, a lot of physics and gambling starts to make sense. So let us start with a simple slope. This slope could essentially just be y equals x. A 1-to-1, as x changes by 1, y changes by 1. Given this y equals x, or something similar, straight line, slope, we get an area of a triangle. What is the area of the triangle? In order to help solve this, what we could do is first, let's define where we're going to start, our interval, right? If we're doing antiderivatives, we're on an interval I, which goes from some point to some point. So let's start from A, and we will go to B. So what we're going to do here is we're going to fill up this empty area with rectangles. We can have the rectangles touch at their leftmost point, their rightmost point, or in the center. And then we can keep that in mind and do calculations for actually where we are touching the line at a later point. But all we need are rectangles that all touch the line at the same corner or middle. So let's pick, in this case, that they're all going to touch in the center of our rectangles. And we fill our rectangles up. Broop, 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 broop. So if we take all of these rectangles and we add them up, we're going to get a pretty good approximation for the area. Because we know the area of each rectangle. And so all we're going to be missing are those little triangles that are hiding inside. But for the most part, we have the area of the slope. And so we write the area is equal to the limit as n approaches infinity. So n will be the number of rectangles that we use. And then we will sum up. So this symbol is the summation symbol. If you see that, it means add up everything after it. So we're going to add up how many n rectangles. And we're going to start at, it will tell us on the bottom, at I equals 1. So we're going to start at rectangle 1. That makes sense. Starting at rectangle 1, counting until you reach rectangle n, sum up what? F of x, so that's y, so that's our height. That's the height of a rectangle, times the change of x. So that's the run, or the base. So the area is equal to the base times the height of each rectangle added together, and then we stick this limit on it so that we could take n all the way to infinity, meaning that we can have different amounts of rectangles. So let us flesh out some of this mathematics. We have delta x, that's the Greek letter delta. Now, it's not just a triangle, it's a letter. Delta x equals, it's the change of x. Well, what is the change of x? It's the point B to A divided by the number of triangles, or the number of rectangles. Because there's going to be an equal amount, they're all equal size, so that change will always be the same. So we can find it as the distance from B to A divided by how many rectangles there are. That's how much change there is. That's how much the base is of each. The xi that goes into the function is that A, so starting at A, plus the change of x. So starting at A, walking one base, and doing that for times I, the number of rectangles we're counting. And so this gets us some nice approximation of the area. But it would be a better approximation if we make more rectangles fill this space. So let us get a quick visual of this. If we fill up this whole area with one single rectangle, we would get that the base, the delta x, is b minus a, from b to a, divided by 1, which is just the space of one rectangle. The x1, so that means there's one rectangle. So 1 times the base plus a, so starting at 0, moving one base, that will be the base that gets plugged into the formula for height, the f of x. So our area, f of x times the change of x, that's our area of one rectangle. And this is not a very good approximation. It's pretty good, but we're off by like half. So what happens then if we just make one rectangle? If we do one rectangle, then the change of x, b minus a divided by 2, we would get half the base of the original of that 1. Make sense? We would go then from 0 to half a base, and then there's 2 x values, and we add them together. And so we get these different functions, and we're getting an approximate area, but it's still not great. So the major idea then being that we want n to approach infinity. All right, if we imagine, let's do one where the rectangles are very small, you can barely see the triangles at all. So we're getting closer and closer the more rectangles we add. So what we have here, in a sense, is since we have a interval from B to A, which is set really firmly in stone here, it's from B to A, we call this a definite integral. So we want to know the definite area of this space. And we write a integral formula. So we make this squiggly line, this S-like symbol, and we put A to B, from A to B. That's our interval. So it's kind of, the squiggle represents, in a sense, a function. This squiggly function, which is going from A to B. And it represents the function f of x. And we want to know one last thing in order to finish a integral. How much does it change? Because that's what matters the most. Dx. It changes by dx every time. And then so we get the actual definition of that being that the integral of f of x changing by dx from A to B or B to A is actually, in one sense, just the summation of a bunch of areas all added together as n approaches infinity. So as the rectangles become essentially straight lines, and there's an infinite amount of them, we will find the area. And that makes sense. This leads us then to the fundamental theorem of calculus. The fundamental theorem of calculus is, if you have a function, some squiggly line, it will be that the integral from A to B of the function changing by dx, so some squiggly line that changes over x or changes over whatever you're graphing, is equal to the antiderivative of b minus the antiderivative of a, where capital F is the antiderivative of our lowercase f function. Hello class and welcome to University Second Year Calculus. So, one of those things that calculus was being invented for was physics, as we mentioned. Isaac Newton being one of those people that helped invent it. His predecessor, the person who was in charge of the Royal Society before him, and his personal enemy, Robert Hooke, had done things with springs and gave us Hooke's spring equation. Now, Robert Hooke's spring equation is a type of calculus problem. So, we can now use the calculus we used in year 1 in order to help solve physics that were stumping people like Newton and Hooke at the time because they were still working on this calculus. So, we have a spring here, and one thing we know about springs is it has a restoring force, which means when you bounce it, it bounces and springs and compresses and goes back and forth, but eventually it will just put itself back to normal. It doesn't collapse in on itself. It likes to stay at a certain place. You stretch it and it will come back. You squeeze it and it will come back. So that's what we call a restoring force. In order to write a restoring force mathematically, we tend to just write negative. If you make it a negative value, that means it will push back on itself. So, we have this spring going along. We're putting our x-axis for now this way, because we only have one, and we want to deal with x, not y. So Our x-axis is going this way, and so is our spring. So in order to write the restoring force, we write that F equals negative K. K is our spring constant. Negative Kx. One of the people that invented calculus, Newton, told us in physics that force is equal to mass times acceleration. We have here then two different forces, and forces are the same thing. So they should equal each other. One force should be equal to another force. That being that I have a mass, and I can accelerate my fingers, and a spring exists, and it has a force, which is negative kx. And so my mass and acceleration and its spring equation should be able to find balance, such that when I compress it, it presses back, and blah, 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 right? So we should get that mass times acceleration equals the spring constant. So let's solve this in terms of that higher level derivative. So we write that with that acceleration. Acceleration is negative k over m. Okay, we are now officially ready to talk about magnetic fields and electric fields. We're going to start by getting in with direction fields. This is called a first order differential equation. So let us write something here. We write, suppose we have a first order differential equation of the form y prime equals the antiderivative f with respect to x and y, where the antiderivative x and y is some expression in x and y. The differential equation says that the slope of the solution curve at the point xy is on the curve at the antiderivative f with respect to x and y. If we draw short line segments with a slope with the antiderivative f with respect to x and y at several points, the points xy's, the result is called a direction field or a slope field. Now, that is a lot of words, but visually, this is actually very simple. We set up a grid, x, y, right? Going up is y, going left and right is x, we understand that. So we have this field. We box it off, it's our grid space, and since we boxed it off, we're living in this field. We can think about this actually as a farmer's field, where we got a bunch of corn or wheat or canola or whatever you want growing nice and high up into the sky. Maybe it's a bunch of sunflowers, I don't know. But you got yourself a field of tall, stocky, growing vegetation. And a wind blows through it. Which way is the wind blowing? If you were to look down on the field, you could see it. Why? Because each plant is standing at a point xy in the field. And each plant is a short line segment that stands straight up when there's no wind. And so when there's no wind, maybe this is what our graph kind of looks like. We don't see anything. But the wind blows through it, and all of the plants start leaning in the direction of the wind. This is a direction field. The thing about a field like this is when we've mapped it, we could put an object on such a field and be able to track which direction it's going to go. So we're looking at a 2D space. But fields, like electric and magnetic fields, are 3D. So what do we have to do? We have to make ourselves a 3D grid. And then we have to move out a space A, we have to move out a space B, and we have to move up a space C. And we get ourselves some point P of the coordinates A, B, C. The amount of X we move, the amount of B we move, and the amount of C we move. Now, we could always think about this in simpler terms by always thinking in terms of shadows. This ray can leave a shadow on the ground, but it can also leave a shadow on a wall or on the adjacent wall of that. So we could think about a ray in space simultaneously as the summation of all three shadows. So you get then the classic distance formula, but in 3 dimensions. So the norm, the absolute value, P1 to P2, point 1 to point 2, in this case the origin to the point, is equal to, so the square root of the change of x squared plus the change of y squared plus the change of z squared. Now, we can also do circles. If we make ourselves a sphere, so a circle in this direction, a circle in that direction, a circle in that direction, and put a skin over top of it, get yourself a sphere. And we can have that point P being in the exact same location, but on a sphere rather than just in the x, y, z space. When we do this, we have ourselves the equation of a sphere with center C and radius r. And so we will say that the center, instead of what we did A, B, C for the other one, we will use H, K, L. So this brings us to spherical coordinates. Spherical coordinates are the coordinates on a sphere. What does that mean? It means where you are on a sphere or in a sphere. So let's just think about Earth. We're on a sphere. How do we know where we are? You need to know not just your latitude and your longitude, but also the radius of the Earth. You need to know where the ground is. So there's 3 functions: the radius, the longitude, and the latitude. And since we're doing calculus, we also need to incorporate the amount of change of each one of those. So if we clean this up, we can see then that the point is at a final location, that location being the location r, theta, phi. So let us introduce a vector or vector space. So a vector is a mathematical object with a length and a direction. The direction of a vector can be found with the r direction, the ray equaling x amount in the x direction or the I direction, a y amount in the y direction or j direction, and a z amount in the k or z direction. The length, as such, also occupying space, is going to take out that space, and we get that norm value, or r squared. The square root of r squared gets us r, and that gets us the square root of x squared plus y squared plus z squared. Now, again, we've seen this where a vector can be represented by its shadows. So we could write out all of the shadows So let us learn a little vector notation or a little vector mathematics. We have some vector, some line that has a direction and a length, and it's going from A to B. So we say that this is the vector AB, and then we can go from B to C, and that will be the vector BC. So if we then add a point from A to C, that being point AC, we can say that the AB vector plus the BC vector equals the AC vector. We can do the reverse, where going from A to B, if we backtrack and we go in the reverse direction, then our B to C is a negative direction. And so when we go from A to C, we can see that AC is AB minus B to C. Another thing that we can do with vectors is scale them. If we're going from A to B, and it's just this AB line, if we were to make that, say, twice as long, then going from A to B would be 2AB. An important factor about talking about vectors is to find a unit vector. So if we can scale things like AB to 2AB, sometimes we won't know when running into things in the wild if they are scaled up. So first, let's talk about a vector. A vector is made up of components. The components of different directions. And we're just going to call them A. That way we can go beyond 3. In order to find a unit vector, what we do is we set C, let C equal 1 over the length. And then we say then that the length of the unit vector is C times the norm of A. So the length of the vector, times this C that we've set is what we call the unit vector. And it then is 1 over the length of A times the length of A, which is equal to 1, the unit vector. Now, if we drop the length of the unit vector, because the length of the unit vector is just going to be 1, that's the point, we drop that, then we also drop that second length of A, and we end up with the unit vector, not the length of it, but the unit vector itself is 1 over the length of the vector times whatever the vector is right now. So that, in a sense, gets us the length plus direction divided by unit length. So one of the important things when talking about vectors, and we've talked about it already, are those shadows. We saw it both on the sphere and without the sphere, when just adding it up in the little rectangle system. So we need to talk about dot products. That is what makes a shadow. So a dot product makes that length, or it makes that shadow. And we say then that if A is a vector, and it is a vector with the components A1, A2, and A3, and we have another vector, B, with the components B1, B2, B3, then the dot product of the vectors A and B is the number that we get when we go A dot B, which is given by the dot product then is A dot B equals the first components multiplied together, A1, B1, plus A2, B2, plus A3, B3. And that gets us just a number. And we get ourselves a theorem out of this. Theorem. If theta is the angle between those two vectors, then the dot product of A and B is the length of A times the length of B times cosine theta, which is what we saw when we were doing our sphere, and we saw that our cosine theta for the Z, that was in a sense the shadow of the ray of a certain length being cast on the wall gave us this new length. And therefore, since this deals with shadows in that way, if a dot b equals 0, then they're perpendicular. If they're perpendicular, then a dot b is 0. Next, the cross product. So a dot b was a form of multiplication that gave us a number, which is, in a sense, gave us a length. But vectors come in two parts. Vectors come in length and direction. So we need a second form of multiplication that gets us out a direction as well. And that's what the cross product does. It makes a vector. So we take our two vectors that we had before, a and b, with components a1, a2, a3, and b1, b2, b3, and we cross product them. And we get the vector a cross b, which is given by a vector component form a2 times b3 minus a3 times b2. That's component 1. So that's the first value. Now there's a second value. That's that y value. So we did x, y, z. So we're on y. The y value is a3 b1 minus a1 b3. And the z component then being a1 b2 minus a2 b1. This gets us a right-hand rule, which is that a, say this is a, is perpendicular to b, say that's b, and that's going to be perpendicular to a cross b, say, which say is the thumb. Or if you do, these two, a and b, then it doesn't really matter. But the point being that vector a and vector b make a third vector which point perpendicular to each other. And you get yourself an orthogonal basis. You get yourself this little right-hand rule. So, we get a theorem. If theta is the angle between a and b, then the length of a cross b is the length of a times the length of b times sine theta. And so then we find a and b are parallel if and only if the cross is 0. And if the cross is 0, then they're parallel. We can now move on to vector functions and space curves. If we take a vector r of t, whose three components are made up of other functions, we would write if vector r of t equals the components f of t, g of t, h of t, then we could say that the limit as t approaches a of that vector would give us the limit as t approaches a for the function f of x, the limit as t approaches a of the function g of t, and we would get the limit as t approaches a of h of t, provided that the limits of the component functions in fact exist. This gives us space curves. Suppose the f, g, and h are continuous real-valued functions on an interval I. Then the set C of all points x, y, and z in space where x equals f of t, y equals g of t, z equals h of t, and t varies throughout the interval I, is called the space curve. If we find the slope of this curve, the limit as h approaches 0 of the vector function r t plus h minus r of t all over h. We could then say if you have a vector function such as the vector r of t, which is equal to the functions f of t, g of t, h of t, we could then rewrite this as f of t I hat plus g of t j hat plus h of t k hat. We also have that the slope of the vector function r prime of t would be f prime of t I hat plus g prime of t j hat plus h prime of t k hat. And we should also be able to do this with integrals in the same way. We can take these into the next lesson. Functions of two variables. Definition. A function of two variables. A function of two variables is a rule that assigns to each ordered pair of real numbers x and y in a set D a unique real number denoted f of x and y. The set D is the domain of f, and its range is the set of values that f takes on. That is, f of x and y is such that x and y belong to the domain. Definition. If f is a function of two variables with domain D, then the graph of f is the set of all points x, y, z in R3, such that z, or z, equals f of x, y, and x, y is in the domain. We can take these to find level curves. Level curves. Definition. The level curve of a function of two variables are the curves with the equations f of x equals k, where k is a constant in the range of f. This is what allows us to map out geographic hills and mountains onto flat plane maps. You can take the space curves of hills, mountains, and valleys and convert them down into a map with these level curves by using k as a constant. Let us quickly talk about a partial derivative. A partial derivative is one where you take the function with two variables and you only take a derivative of one of those two variables. So, definition in math terms, the partial derivative fx of ab is equal to g of a, where g of x equals f of xb. And we can write fx, or the partial derivative with respect to x, of the function with respect to xy, is equal to the limit as h approaches 0 of f a plus h b minus f of ab all over h. And likewise, the partial derivative with respect to y of the function with respect to x and y would be the limit as h approaches 0 of f a b plus h minus f a b over h. We can then do what is called higher order derivatives, where we do partial derivatives twice. And so we can take that first partial derivative, fx, and make it have another partial derivative with respect to x. And we could write fxx, which is the partial derivative with respect to x of the partial derivative of f with respect to x. Or we could write di squared f over di x squared. When we go through each one of them, we get a little bit of change up. We get fy of x, so we would get which we could write fyx. So in this case, we would have the partial derivative with respect to x, and then the partial derivative of f with respect to y. Or we could write di squared f over di x di y. In the reverse case, fx then partially derived by y, or fxy, would be di over di y times di f over di x, or di squared f over, and these flipped, di y di x. The fyy is the exact same as fxx, but now we get di squared f over di y squared. This then brings us to the wave equation. The wave equation is di squared u over di x squared plus di squared u over di y squared, which is equal to 0. This then brings us to the wave equation. This wave equation is something that we could have found during our conversation about Hooke's springs. In the Hooke equation, we found that acceleration is equal to some constant times x. X being the current position of the spring. Acceleration is the change in velocity over time, and velocity is the change of position over time. This kind of equation that we get from Hooke can be turned into the wave equation, which says di squared u over di t squared, so it's basically kind of like an acceleration, is equal to a squared times di squared u over di x squared, so the wave's displacement. So this matches almost exactly with kind of what Hooke's law looks like, where the a squared would take the place of negative k over m. And the position of x is being replaced here by a partial derivative, or a higher order partial derivative. And here we can say, in the case of a wave, say a sinusoidal wave, that u, the function that we're using to represent the wave, which comes in two components, x and t, it changes in where it is over time, which is equal to some sine wave x minus a times t. When we add that third dimension on to the other equation, we could call this Laplace's equation in 3 dimensions. We then move on to directional derivatives. Definition. The directional derivative of x at x null, y null, in the direction of a unit vector, vector u equals the components a, b, is the directional derivative f x null, y null is equal to the limit as h approaches 0 of the function x null plus ha, y null plus hb minus f x null, y null all over h. Theorem. If f is a differentiable function of x and y, then f has a directional derivative in the direction of any unit vector, vector u being made of the components a, b, and therefore the directional derivative of f with respect to x and y would be equal to the partial derivative of f with respect to x and y times a plus the partial derivative of y with respect to xy times b. This gives us the gradient vector. We start with the directional derivative of f with respect to x and y, which is equal to fx of x and y times a plus fy of f and x times b. And we separate the two components such that we get that the directional derivative is equal to the components, which are the partial derivative with respect to x and the partial derivative with respect to y, times the components a and b. And that a and b are converted into the vector components u. Components of partial derivatives can be simplified into a single symbol, which is an upside-down triangle called nambla. This formalization tells us that we have the partial derivative of f with respect to x in the I direction plus the partial derivative of f with respect to y in the j direction. So we get that the directional derivative of f is equal to nambla f times the vector unit u. This then gives us the definition of what a gradient vector is. Definition. The directional derivative of f at x null, y null, z null in the direction of a unit vector, vector u, which is made of the components a, b, c, is the directional derivative of f with respect to x null, y null, z null, and is equal to the limit as h approaches 0, f of x null plus ha, y null plus hb, z null plus hc, minus the function x null, y null, z null all over h, if this limit exists. So we get the gradient vector is nambla f equals the components, the partial derivative of f with respect to x, the partial derivative of f with respect to y, the partial derivative of f with respect to z, which we can also write as di f over di x I plus di f over di y j plus di f over di z k, giving us our three dimensions of space. And therefore, we can also write that the directional derivative of f x y z is equal to nambla f x y z times the unit vector u. We can take all of this to find vector fields. Definition: let D be a set in R2, a plane region. A vector field on R2 is a function, capital F, that assigns to each point xy in D a two-dimensional vector, capital F, of xy. The vector field fxy is equal to p of xy in the I direction plus qxy in the j direction. Let E be a subset of R3. A vector field on R3 is a function, capital F, that assigns to each point xyz in E a three-dimensional vector, capital F xyz, such that we get the vector field capital F xyz is equal to the components p xyz in the I direction plus q xyz in the j direction plus r xyz in the k direction. And this brings us back to our conversation about those wires on the table. Here is a real-life example: electric force. We have here the electric force, which we have capital F hat with respect to the three dimensions xyz is equal to epsilon times q times capital Q all over the distance away from the two charges, x to the power 3, we're in three dimensions, times x hat, which is the direction that they are away from each other. Because we have a vector, we have two equations. We have the x hat, which tells us that we have three dimensions, how much distance they are x apart in the I direction, how much they are apart y in the j direction, and how much they are apart z in the k direction. And we have the length, the actual physical distance, which is the square root of x squared plus y squared plus z squared. So we can reformulize capital F hat to equal epsilon q times q, and then we have the x hat over the length. We can break this up into their three components, so we write this 3 times. So then the tops of each would just be epsilon q q x I over the distance plus epsilon q q y j over the distance plus epsilon q q z k over the distance. The electric field is what happens when you take the electric force and you divide by one of those two charges, that meaning you, in a sense, pretend you are that charge. You don't feel your own force. So what you feel is the field. That's the same as the capital F hat divided by, say, little q in this case. So we just get epsilon q over the distance times that x hat, which we can break down in that same way. If we break down the equation of the electric field, capital E is a shorthand that represents a function which can move in all three real-world directions, so east to west for x, y being north to south, z being up and down. And what is a function? A function is any pattern that changes results when you change its inputs, meaning E changes if you change x, y, and or z. The epsilon q. Epsilon is the permittivity of free space, which was discovered as electric fields are resisted by different medium. And a medium, a vacuum of free space, so the universe outside of Earth, the ether, the vacuum, free space, whatever you want to call it, was measured to have an electrical permittivity of 8.854,187,8188 times 10 to the negative 12 coulombs squared over kilograms over meters cubed times seconds squared. Q is just the charge of the charged particle at the origin of the field. Xi plus yj plus zk, this is merely the linear equation y equals x. However, this is linear in all three dimensions. Therefore, you can easily read this as moving out from the origin in all directions, like arrows describing the direction of air from an explosion, all pointing from the origin outward in straight lines. And finally, we have the square root of x squared plus y squared plus z squared cubed. This is the unit distance from the origin to the point. But since it is moving a unit distance away in 3 dimensions, we have the distance 3 times, raising us to the third power. The unit distance is just triangle math. And thus we have come to a full conclusion. We now have the electric field that we needed to talk about the wires at the very beginning. And we got here, essentially, just by talking about triangles and circles. So let us return to our electric field example. We start with our plot, x and z. There is some point above one of the ends of the wire where we are trying to find the electrical field. Let's imagine that we lay the length of wire down on the x-axis, and it goes from 0 to L, the length of the wire. Every point on the wire will point towards this electrical field to some degree, and for simplicity's sake, we can just make it the very end of the wire. This gives us some vector, a cursive r in this case, which is composed of 2 units, the vector r, which is the z-axis, and the vector r prime, which is on the x-axis. Let us start with the given information that we know. We have lambda, which is the uniform line charge, the current going through the wire. Lambda, in this case, would be the total charge of the wire divided by the length of the wire. L being the length of the line segment or the length of the wire. And we have Z, the height above one of the ends of the wire. And we are looking for the electric field above one of the ends of that wire at the point Z. So here we can see our 2 R's. The vector R is the amount of Z we travel in the Z direction, and the R prime vector is the amount of X we travel in the X direction. So let us deal with some facts. One fact that we can learn through observation is that the electric field is proportional to the inverse of the surface area. Another such fact that we can learn through observation is that the electric field is proportional to the inverse of the distance squared. A third fact is that the electric field is proportional to the inverse of the resistance. And we can also learn that the electric field is proportional to the charge. Given these facts, we can move on to another fact, that the electric force is a test charge Q times that electric field, which is the test charge Q times something which is inversely proportional to surface area, inversely proportional to resistance, and that inversely proportional distance squared, that cursive r squared. The rest of the E is the sum of all of the charges in the direction of that cursive r. So, what is the surface area? What is the resistance? What is the charge? We could take the summation sum and turn it into an integral from 0 to L. And that would give us the different dq's, the changes in q, over the distance squared in the direction of r. Let us deal with charge, given the facts we know. The electric field in the direction of the cursive r should be proportional to 1 over the surface area, the resistance, and the distance squared, all times q. So let's just take out right now the surface area and the resistance. And we take the integral of dq over the distance squared in the r direction. We know from our formula of lambda that lambda is the charge over the distance, and we can reverse that and find that the change of charge is equal to the uniform line charge times the small changes along x. So we get the integral from 0 to L is lambda dx over r squared. Next, let's find the resistance. The resistance can be found through scientific observations using different media. When you remove all of the media, you create a vacuum, you still find an electrical resistance. And we're just going to borrow from the Wikipedia of the resistance of free space. Vacuum permittivity, epsilon naught, is the value of the absolute dielectric permittivity of classic vacuum. Epsilon naught is 8.854187888 times 10 to the negative 12 farads per meter, and it is a measure of how dense of an electric field is permitted to form in response to electrical charges, and relates the units of electric charge to mechanical qualities, such as length and force. For example, the force between two separated electrical charges with spherical symmetry in the vacuum of classical electromagnetism is given by Coulomb's law, which is equal to charge 1 times charge 2 over 4 pi epsilon naught r squared. The 4 pi comes from that spherical symmetry, and we will see that in the next section here. We will solve the surface area in the next slide, but for now we could say that we have 1 over the surface area times epsilon naught times r squared, and this inverse section is times by the charge q. So let us now move on to surface area. Let us take a sphere. The charge sits at the center of this XYZ axis, and its electrical field spreads out in all directions a distance rho. It moves off the angle z through theta, and it moves off the axis of x through phi. So we can convert our Cartesian axis of xyz into spherical coordinates of rho, theta, and phi. We can break this into parts for simplicity's sake, and we look at the xy ground, the plane that those two sit on together, as a single line. We're looking at it from an angle. So we have the plane xy, and we have the z-axis pointing up. Between these 2 points, we have the distance rho. That rho leaves a shadow on the ground, s, and the height that the rho goes up, we can call z. The angle that rho has off of the axis of z is a difference of theta. And given geometry, I believe we learned in grade 9, if this is theta here, then to go all the way back down is to have another theta in symmetry form. Given this theta, we can have opposites and adjacents, and hypotenuses. So we have that the sine theta is the shadow over the vector rho, and the cosine of the theta is the height z over the distance rho. We can find a second vector here. If we look down at the xy plane, we would have the x-axis and the y-axis, which are perpendicular to each other, and we can draw out the shadow that lies on the floor. And this s is composed of how far y we go up and how far x we go right. The angle that the shadow has off of the x-axis we can define by a change of phi. And note here that we know that the distance s should equal the square root of x squared plus y squared. So we can write sine phi is y over s, and cosine phi is z over s. If we change this around, we can find that s equals rho sine theta, z equals rho cosine theta, y equals s sine phi, and x equals s cosine phi. Every place that we have an s, we can plug in that first value of rho sine theta, so our Cartesian coordinates are converted.
x now equals rho times sine theta cosine phi. Y equals rho times sine theta sine phi. And z equals rho cosine theta. And therefore, our vector r should be the square root of s squared plus z squared. And we know what s squared is. So altogether, we know that the length of r is the square root of x squared plus y squared plus z squared. If we want to do our electrical field in spherical coordinates with this r, then it is the square root of rho squared sine squared theta cosine squared phi plus rho squared sine squared theta sine squared phi plus rho squared cosine squared theta. Let us quickly discuss the gradient of r, which is essentially how one discovers how to go down a hill. The gradient of r is the amount of change of r with the amount of change of x in the x direction plus the change of r with respect to the change of y in the y direction plus the change of r with respect to the change of z in the z direction. And the magnitude of this r is the square root of x squared plus y squared plus z squared. So let's find the change with respect to x of the magnitude r. This would be the change with respect to the change of x squared plus y squared plus z squared to the power of 1/2. This partial derivative will result then in 1/2 times x squared plus y squared plus z squared to the power of negative 1/2 all times 2x, which we can rewrite as x over the square root of x squared plus y squared plus z squared. And this pattern repeats for the change with respect to y and the change with respect to z. So we can put this all together and say that the gradient of r is the amount of x we move in the x direction over the square root of x squared plus y squared plus z squared plus the amount of y in the y direction over the square root of x squared plus y squared plus z squared plus the amount of z in the z direction over the square root of x squared plus y squared plus z squared. Given that the denominators are all the same, we can put them together and we'd have the amount of x in the x direction plus the amount of y in the y direction plus the amount of z in the z direction all over the square root of x squared plus y squared plus z squared, which can be represented as the direction of r over the length of r. Now let us do something similar for our spherical coordinates. We're going to take r, which is rho sine theta cos phi, rho sine theta sine phi, and rho cos theta, and let us take the derivative with respect to rho for each one of these. So we would get sine theta cos phi, sine theta sine phi, and cos theta. If we take the difference of r with respect to the differences in theta, we would get rho cosine theta cosine phi, rho cosine theta sine phi, and negative rho sine theta. And we take the difference with respect to phi. We would get negative rho sine theta sine phi, rho sine theta cosine phi, and 0. So the derivative of r is the magnitude of the derivative of r with respect to rho, d rho in the rho direction, plus the magnitude of the change of r with respect to theta, d theta in the theta direction, plus the magnitude of the change of r with respect to phi, d phi in the phi direction. Given that we're working with a wire, we're going to use line integrals. So we're going to say dl, the symbol usually for line integrals. In this case, with respect to rho, we can say that the magnitude of dr over dp is equal to the square root of sine theta cos phi all squared plus sine theta sine phi squared plus cosine squared theta. We'll just move the square into all of these brackets. We can then take sine theta out of the first two units so that we have sine squared theta times cosine squared phi plus sine squared phi. And when we have a sine squared plus cosine squared of the same unit, that is equal to 1 squared or just 1. So that reduces down to sine squared theta times 1 plus cosine squared theta. The 1 disappears and we're left with sine squared plus cosine squared of the same unit. So it's another 1. So we get the square root of 1, which is 1. And so the magnitude of r with respect to phi is equal to 1. We could also say that the dr with respect to rho is equal to d rho. If we do the same procedure with respect to theta, we get that this equals the square root of rho cosine theta cosine phi all squared plus rho cosine theta sine phi all squared plus negative rho sine theta squared. Simplifying by moving this 2 to all of the positions, we cancel out that negative 1. From the first two entries, we can take out rho squared cosine squared theta, and we're left with, in brackets, cosine squared phi plus sine squared phi, which is 1. Which leaves us then with the square root of rho squared cosine squared theta plus rho squared sine squared theta. So we take the rho squared out, and we have cosine squared plus sine squared, which is 1. And so then the dr, the change of r with respect to the theta direction, is equal to rho d theta. Let's do this one more time for the phi. In this case, we only have the first two entries, as that last entry derived to 0. So we have the square root of negative rho sine theta sine phi all squared plus rho sine theta cos phi all squared. Move these squares into those brackets, and we get the square root of rho squared sine squared theta sine squared phi plus rho squared sine squared theta cosine squared phi. We can take out a rho squared sine squared theta, and we have ourselves sine squared phi plus cosine squared phi in brackets, which is 1, leaving us with the square root of rho squared sine squared theta, which is just equal to rho times sine theta. So our dr with respect to phi is rho sine theta d phi. Now we take our electrical field, which is in respect to r, in this case in our spherical coordinates, and we found our line integral segments. dl, which is 1, our d theta, which is rho, and our dl phi, which is rho sine theta. Now area is length times width. And in this case, on a sphere, that is the dl theta times the dl phi. And so we will use that to find our surface area. But to simplify this down for now, we have our vector r, which is rho sine theta sine phi in the rho direction, plus rho sine theta cosine phi in the phi direction, plus rho cosine theta in the phi direction. In the small change vector of r, we have d phi in the phi direction, plus phi d theta in the theta direction, plus rho sine theta d phi in the phi direction. Let us quickly return to the gradient of r. We're looking for the surface area, which is the integral of dA, the change of area. That dA is dl theta times dl phi, which from our dr are the elements rho d theta and rho sine theta d phi. So we integrate from 0 to pi and 0 to 2 pi of rho squared sine theta d phi. Rho is a constant here, so we can push it out in front of the integrals and get phi squared times the integral from 0 to pi of sine theta d theta times the integral from 0 to 2 pi d phi. This means that we have a surface area which is rho squared times negative cosine theta from pi to 0 and phi from 2 pi to 0. Rho squared times negative cosine pi plus cosine 0 times 2 pi gets us rho squared times negative 1 plus 1 times 2 squared, which simplifies down to a surface area of 4 pi r squared. Therefore, our electrical field is 1 over 4 pi epsilon naught r squared times the charge. So let us return back to our electrical field. Let's redraw our map. On our map, let's put our little dq equals lambda dx. And we have figured out that E, which was 1 over the surface area times resistance, times the integral from 0 to L of dq over cursive r squared in the cursive r direction, we can now say is E equals 1 over 4 pi epsilon naught. That's a constant, so it can sit outside the front of this integral. From 0 to L, the wire's length with that lambda dx in that r direction over r squared. And we can replace the cursive r with values that we know, such as z in the z direction minus x in the x direction. And the r on the bottom, we can multiply to that other cursive r and we get r cubed. The lambda is a constant, so it can be moved out in front. So we get that E equals lambda over 4 pi epsilon naught times the integral from 0 to L of the amount of z we changed in the z direction minus the amount of x we change in the x direction, all over cursive r cubed. And of course, this is dx. We're changing direction in the x direction. So let's break this into two parts, the z direction and the x direction, and let's plug in what cursive r is in this, which is the square root of x squared plus z squared. And so we get that E equals lambda over 4 pi epsilon naught times the integral from 0 to L of z in the z direction over the square root of z squared plus x squared cubed dx minus the integral from 0 to L of the amount of x we move in the x direction over the square root of z squared plus x squared cubed dx. We will break this into two parts and call the first section dEz and the second section dEx. So let us start with the EZ direction. The z is a constant in this case, so we can move it out of the integral. Then we get the equation is lambda z over 4 pi epsilon naught times the integral from 0 to L of 1 over x squared plus z squared to the power of 3 over 2 in the dx direction. Doing a little trigonometry, we know that tan theta is opposite over adjacent. And so we can say, for simplicity's sake, let's make x equal z tan theta. In which case, we can say that dx is actually z times secant squared theta d theta. If we make these substitutions, we will get that lambda z over 4 pi epsilon naught times the integral from 0 to L is now z secant squared theta d theta over z squared tan squared theta plus z squared, all to the power of 3 over 2. We could take z squared out of that denominator, and we'd get z squared times tan squared theta plus 1, which is an identity of trigonometry, which is secant squared theta. So then in the numerator, we have z secant squared theta, and in the bottom, we have z cubed secant cubed theta. So we can cancel out all of the repeating numbers, and we get that Ez is equal to lambda over 4 pi epsilon naught z, moving that z out, times the integral from 0 to L of 1 over secant theta d theta. 1 over secant theta is cosine theta. And the integral of cosine theta is sine theta. And this sine theta is going from L to 0. And we know from previous work that this sine theta is equal to x over the square root of x squared plus z squared. So we replace the sine theta with this value, and then we plug in the L and we plug in the zeros. And so we get that Ez is equal to lambda over 4 pi epsilon naught z times L over the square root of L squared plus z squared. Now let's do the derivative of E with respect to x. So that is the lambda over 4 pi epsilon naught times negative x in the x direction over the square root of x squared plus z squared, all to the power of 3 dx. So we're going to take the integral of that so that we can find Ex, and we get negative lambda from moving that negative outward over 4 pi epsilon naught times the integral from 0 to L of x over x squared plus z squared to the power of 3 over 2 dx. Let us do a u substitution to solve this. Let u equal x squared plus z squared. The derivative of such a substitution, du, would be 2x dx. Therefore, x dx is actually equal to du over 2. So let's make this u substitution. Ex is equal to negative lambda over 4 pi epsilon naught times the integral from 0 to L of du over 2u to the power of 3 over 2. We can move the half out of the integral and get the integral of du over u to the power of 3 over 2. This gives us the result of negative lambda over 4 pi epsilon naught times 1/2 times negative 2 over u to the power of 1/2, or the square root of u, from L to 0. If we get rid of the u substitution and we put back in the x squared plus z squared, we get that Ex is equal to negative lambda over 4 pi epsilon naught times 1/2 times negative 2 over the square root of x squared plus z squared, and we have to plug in our L and our 0. If we do some cancellations, we simply get lambda equals 4 pi over epsilon naught times 1 over the square root of x squared plus z squared, and we have to plug in L and 0. If we plug in the L, that x is replaced by L. If we plug in the 0, the x is replaced by 0. Both work. And so we get a two-part answer here, and we get that E, with respect to x, is equal to lambda over 4 pi epsilon naught times 1 over the square root of L squared plus z squared minus 1 over the square root of z squared, which we can obviously cancel the square root of z squared and just get 1 over z. And therefore, we can take the Ex and the Ez and put them back together to find our E, our electric field. The electric field, the final solution then, is E equals lambda over 4 pi epsilon naught times, in the x direction, 1 over the square root of L squared plus z squared minus 1 over z. And in the z direction, 1 over z times L over the square root of L squared plus z squared, which otherwise could be written as E equals lambda over 4 pi epsilon naught times 1 over the square root of x squared plus z squared minus 1 over z in the x direction, plus L over z times the square root of L squared plus z squared in the z direction. And this is the solution to the electric field, and we have discovered it by starting at kindergarten and working all the way to 3rd or 4th year university calculus. And now we have come to the full completion of the electrical field of this wire.